Hey there. Imagine stepping back in time to an era when the very air you breathed could kill you, not from pollution or toxins, but from having too much of what keeps you alive. Picture a world where dragonflies cast shadows like small aircraft and millipedes grew longer than school buses. This isn't science fiction. This is Earth 300 million years ago, during a period so rich in oxygen that it fundamentally rewrote the rules of biology. Tonight we're diving into the Carboniferous period, an age when our planet became a laboratory for gigantism, producing creatures so massive they challenge everything we think we know about the limits of life. So grab something comfortable, maybe dim those lights, and let's journey back to when insects ruled the skies and the very atmosphere was a drug that turned tiny creatures into titans. The year is roughly 320 million years ago. The continents are slowly merging into what geologists call Pangea, and Earth looks nothing like the world we know today. Vast tropical forests stretch across landscapes that will one day become Europe and North America. These aren't ordinary forests. They're dominated by towering tree ferns, massive club mosses, and primitive conifers that create dense, humid canopies dripping with moisture. The air itself feels different here, thicker somehow, almost intoxicating, and for good reason. While our modern atmosphere contains about 21% oxygen, the Carboniferous atmosphere was pumping out a staggering 35%. That's enough extra oxygen to fundamentally alter how life could exist on this planet. This oxygen bonanza didn't happen overnight. It was the result of a perfect storm of geological and biological events that had been building for millions of years. Those massive forests weren't just growing, they were dying and getting buried before they could fully decompose. Layer upon layer of plant material accumulated in swampy lowlands, eventually forming the coal deposits that give the Carboniferous period its name. As these forests pulled carbon dioxide out of the atmosphere and locked it away underground, oxygen levels soared to heights never seen before or since in Earth's history. But here's where things get interesting. All that extra oxygen didn't just sit there doing nothing. It created an opportunity, a biological opening that life was quick to exploit. And no group of animals took advantage, quite like the arthropods, particularly the insects. See, insects have a fundamentally different respiratory system than we do. Instead of lungs, they rely on a network of tubes called tracheae that carry oxygen directly to their tissues through passive diffusion. It's an elegant system, but it has one major limitation. The bigger you get, the harder it becomes for oxygen to reach the inner parts of your body. It's like trying to breathe through increasingly longer straws. At some point, you just can't get enough air. Under normal atmospheric conditions, this puts a hard cap on insect size. But when oxygen levels hit 35%, that limitation suddenly became much less restrictive. Insects could grow larger and still get the oxygen they needed to power their massive bodies. The result was an evolutionary explosion of gigantism that produced some of the most spectacular creatures ever to grace our planet. Flying through the humid Carboniferous skies was Meganeuromoniae, and calling it a giant dragonfly doesn't quite do it justice. With a wingspan stretching 75 centimeters, nearly 2.5 feet across, this aerial predator was roughly the size of a small hawk. But Meganeura wasn't actually a true dragonfly. It belonged to an extinct order called Meganisoptera, creatures that paleontologists now call griffinflies, to distinguish them from their modern relatives. These weren't just scaled-up versions of today's dragonflies. They were something entirely different, built for a world that no longer exists. The first Meganeura fossil was discovered in France back in 1880, and when French paleontologist Charles Brongniart examined it 5 years later, he knew he was looking at something extraordinary. The name he gave it, Meganeura, literally means large-veined, referring to the intricate network of wing supports that allowed these giants to stay airborne. But it wasn't until much later that scientists began to understand just how these creatures managed to grow so large. Imagine encountering one of these beasts in the wild. Meganeura was built like a precision flying machine, with enormous compound eyes that could track movement across vast distances. Its legs were armed with spines designed to snatch prey out of midair, and it could reach speeds of over 30 kilometers per hour while maintaining the agility to hover, fly backwards, and execute sudden aerial maneuvers that would put modern fighter pilots to shame. This wasn't just a big insect. It was an apex predator that dominated the Carboniferous skies. But Meganeura was just one member of a diverse family of giants. The Dragonflies came in various sizes and hunting styles, from ambush predators that waited motionless on perches to aerial hunters that patrolled vast territories like feathered raptors. Some species had wingspans approaching 71 centimeters, making them larger than many modern birds. These weren't clumsy giants either. Analysis of their wing structure suggests they were incredibly sophisticated flyers, capable of complex aerial maneuvers that modern dragonflies can only dream of. The key to understanding these creatures lies in recognizing that they lived in a fundamentally different world. The atmospheric composition alone would have killed most modern animals within minutes. That 35% oxygen concentration wasn't just beneficial, it was essential for supporting their massive respiratory needs. Modern insects simply couldn't survive in such an environment, and Carboniferous giants couldn't survive in ours. They were perfectly adapted to their hyperoxic world. But that adaptation came with a price. Yet the oxygen story isn't as simple as it initially appears. For decades, scientists assumed that high oxygen levels merely allowed insects to grow larger by making their respiratory systems more efficient. But recent research has revealed a much more complex relationship. Some paleobiologists now argue that insects didn't just grow large because they could. They grew large because they had to. High oxygen levels, while beneficial for adults, could be toxic to developing larvae that couldn't regulate their oxygen intake. Growing larger helped these juvenile insects avoid oxygen poisoning by changing their surface area to volume ratio, effectively diluting the amount of oxygen they absorbed relative to their body size. This oxygen toxicity hypothesis helps explain some puzzling aspects of Carboniferous gigantism. Giant insects didn't disappear immediately when oxygen levels began to decline. Some massive Dragonflies persisted well into the Permian period, even as atmospheric oxygen dropped significantly below Carboniferous peaks. If oxygen availability was the only factor limiting insect size, these giants should have vanished as soon as oxygen levels fell. Instead, they managed to survive for millions of years, suggesting that the relationship between atmospheric composition and body size was more nuanced than originally thought. The story becomes even more intriguing when we consider what else was happening in Carboniferous ecosystems. This was a world without flying vertebrate predators. Birds wouldn't evolve for another 150 million years, and pterosaurs were still tens of millions of years in the future. The skies belonged entirely to arthropods, and without the pressure of aerial predation, there was little evolutionary incentive for insects to remain small and agile. Size became an advantage rather than a liability. Larger insects could take down bigger prey, defend larger territories, and dominate their smaller competitors. But the Carboniferous giants weren't limited to the skies. Crawling through the humid undergrowth was perhaps the most spectacular arthropod of all time. Arthropleura, a massive millipede-like creature, stretched over 2.5 meters in length and weighed as much as a large dog. This wasn't just big for an invertebrate. This was big, period. Imagine encountering something the size of an American alligator, but with dozens of jointed legs and an armored exoskeleton that could deflect almost any attack. Arthropleura remains one of paleontology's most fascinating puzzles. For over a century, scientists found plenty of body fossils, but they were almost always headless molted shells that revealed little about the creature's anatomy or lifestyle. It wasn't until recently that researchers finally discovered intact juvenile specimens that preserved the head and mouth parts, revealing unexpected features like crab-like eye stalks that suggest a more complex life history than anyone had imagined. These giants left behind massive trackways in Carboniferous sediments, some over 50 centimeters wide, providing direct evidence of their movements across ancient landscapes. The tracks suggest that despite their impressive size, Arthropleura moved slowly and deliberately, probably feeding on the abundant plant debris that littered the forest floor. Some paleontologists have even attributed enormous burrows to these creatures, suggesting they may have hibernated underground during unfavorable conditions. What makes Arthropleura particularly remarkable is how it achieved its massive size. Unlike many arthropods that are born with their full complement of body segments, Arthropleura appears to have added segments throughout its growth, gradually building up its enormous length over time. This developmental pattern is similar to modern millipedes, but represents it taken to an almost absurd extreme. The largest specimens had around 30 body segments, each covered with 3 protective plates and bearing multiple pairs of jointed legs. The discovery of Arthropleura has revolutionized our understanding of terrestrial arthropod evolution. Here was an invertebrate that had achieved sizes comparable to large vertebrates, proving that the arthropod body plan could be scaled up far beyond what anyone thought possible. But like the giant flying insects of its time, Arthropleura was perfectly adapted to Carboniferous conditions and couldn't survive the changing world that followed. These Carboniferous giants weren't just biological curiosities, they were keystone species that shaped entire ecosystems through their feeding, movement, and interactions with other organisms. The massive trackways and burrows they left behind altered soil chemistry and hydrology. Their predation pressure influenced the evolution of prey species. Their very presence changed the fundamental dynamics of terrestrial and aerial food webs in ways we're only beginning to understand. The world that supported these giants was itself a marvel of biological engineering. The vast coal swamps that covered much of the tropical regions were unlike any modern ecosystem. Tree ferns towered 40 meters into the air, creating multi-layered canopies that supported an incredible diversity of arthropod life. Club mosses reached the size of modern trees, and primitive seed plants were just beginning to experiment with the innovations that would eventually lead to flowering plants. This was a world of extremes where the very air could support life forms that seem almost mythical by today's standards. But it was also a world in transition, balanced on the edge of dramatic changes that would reshape life on Earth forever. The giants of the Carboniferous were living on borrowed time, sustained by conditions that couldn't last forever. The chemistry of this ancient atmosphere tells a story that's both beautiful and terrifying. That extra oxygen didn't just float around harmlessly. It was a reactive, almost aggressive molecule that could damage living tissue at high concentrations. For modern animals, breathing 35% oxygen for extended periods would cause cellular damage, vision problems, and eventually convulsions. Yet somehow, the arthropods of the Carboniferous not only survived in this environment, they thrived in ways that seem almost impossible by today's standards. Recent research into how juvenile insects handled these extreme oxygen levels has revealed something fascinating. Unlike adult insects that can control their oxygen intake through specialized breathing holes called spiracles, larvae typically absorb oxygen directly through their skin. They have no way to regulate how much of this potentially toxic gas enters their bodies. In the hyperoxic world of the Carboniferous, this created a serious problem. Too much oxygen could literally poison developing insects before they reached adulthood. The solution was counterintuitive. Growing larger actually helped protect these juvenile arthropods from oxygen toxicity. As body size increases, surface area grows more slowly than volume, following a basic principle of geometry. A larger larva would absorb proportionally less oxygen relative to its total body mass than a smaller one, What appeared to be a size advantage may have started as a survival mechanism against the very atmosphere that sustained adult life. This discovery helps explain some of the mysteries surrounding Carboniferous gigantism. Scientists studying modern stonefly larvae, which live underwater like many ancient insect juveniles, found that young specimens are far more sensitive to oxygen fluctuations than their terrestrial adults. The parallels to Carboniferous conditions are striking. Higher atmospheric oxygen means higher concentrations dissolved in water, creating potentially toxic conditions for aquatic larvae that couldn't regulate their gas exchange. The implications extend far beyond simple respiratory physiology. If insects grew large primarily to avoid oxygen poisoning in their youth, then the relationship between atmospheric composition and body size becomes much more complex. It suggests that Carboniferous giants weren't just taking advantage of abundant oxygen. They were adapting to survive in an environment that was simultaneously life-giving and potentially lethal. But the oxygen story interweaves with other factors that shaped this extraordinary period. The absence of flying vertebrate predators created an ecological vacuum that arthropods rushed to fill. Without birds, bats, or pterosaurs patrolling the skies, there was no evolutionary pressure for insects to remain small and maneuverable. Size became a pure advantage, allowing creatures like Meganeura to dominate aerial ecosystems without fear of being outmaneuvered by faster, more agile vertebrate hunters. This predator-free environment lasted for tens of millions of years, providing ample time for arthropods to evolve increasingly spectacular forms. The Dragonflies developed into a diverse array of aerial specialists, each adapted to different hunting strategies and ecological niches. Some were ambush predators that waited motionless among vegetation. Others were active hunters that patrolled vast territories with the persistence of modern raptors. The largest of these aerial giants belonged to a species called Meganeuropsis, which lived during the early Permian period and boasted wingspans reaching 71 centimeters. These creatures pushed the absolute limits of what was possible for flying arthropods, representing the pinnacle of insect gigantism before changing conditions brought their reign to an end. Understanding how these giants actually flew requires appreciating the sophisticated engineering of their wing systems. Unlike modern dragonflies, Dragonflies lacked certain specialized wing features that characterize true dragonflies today. Their wing venation patterns were simpler but incredibly robust, designed to handle the stresses of powering massive bodies through dense, humid air. The wings themselves were marvels of biological architecture, with intricate networks of supporting veins that provided both strength and flexibility. Flight performance analysis suggests these giants were surprisingly capable aerial athletes. Despite their size, they could achieve remarkable speeds while maintaining the ability to hover, reverse direction, and execute complex maneuvers. Their enormous compound eyes provided exceptional visual acuity over long distances, allowing them to spot prey and rivals from hundreds of meters away. The combination of size, speed, and visual capability made them virtually unstoppable apex predators in Carboniferous skies. Yet for all their aerial dominance, the Dragonflies were products of very specific environmental conditions. Their respiratory systems were finely tuned to extract maximum efficiency from oxygen-rich air. Their wing loading, the ratio of body weight to wing area, was optimized for dense atmospheric conditions that no longer exist. When those conditions began to change, these magnificent creatures found themselves increasingly out of sync with their environment. The terrestrial giants faced similar challenges, but from different angles. Arthropleura's massive size came with significant trade-offs that worked well in Carboniferous ecosystems, but would prove problematic later. Moving a body over 2 meters long required enormous amounts of energy, especially through the dense vegetation of coal swamp forests. The creature's slow, deliberate movements suggest it was built more for endurance than speed, perfectly suited to a world where size alone provided protection from most threats. Recent discoveries about Arthropleura's anatomy have revealed unexpected complexity in these seemingly simple giants. The juvenile specimens found in French fossil deposits showed crab-like eye stalks that differ dramatically from anything seen in modern millipedes or centipedes. This suggests a more amphibious lifestyle than previously thought, with young Arthropleura possibly spending time in aquatic environments before transitioning to fully terrestrial adults. The developmental pattern of adding body segments throughout growth represents another fascinating aspect of Arthropleura biology. Modern millipedes follow a similar pattern but typically max out at much smaller sizes. Arthropleura took this developmental strategy to its logical extreme, continuously adding segments and legs until reaching its massive adult proportions. The largest specimens had between 32 and 64 legs distributed across their elongated bodies, creating a walking machine unlike anything alive today. These creatures left behind some of the most impressive trace fossils in the paleontological record. Trackways up to 50 centimeters wide snake across ancient sediment layers, providing direct evidence of how these giants moved through their environment. The spacing and depth of individual footprints suggest a surprisingly coordinated gait for such a many-legged creature, with legs moving in waves along the body length to propel the massive animal forward. Even more impressive are the enormous burrows attributed to Arthropleura and its relatives. Some of these underground chambers are large enough for a person to crawl through, suggesting that these giants may have practiced a form of hibernation during unfavorable seasons. The energy requirements for maintaining such a large body would have been substantial, making periods of dormancy a practical survival strategy during times when food was scarce. The ecological impact of these terrestrial giants extended far beyond their immediate feeding activities. Their massive burrows altered soil chemistry and hydrology across vast areas. Their movements through dense vegetation created pathways that other animals could follow. Their feeding on plant debris helped recycle nutrients and organic matter in ways that influenced entire forest ecosystems. But perhaps most significantly, creatures like Arthropleura demonstrated that the arthropod body plan could be scaled up to sizes that rivaled large vertebrates. This challenged fundamental assumptions about the limitations of invertebrate design and showed that, under the right conditions, arthropods could compete directly with vertebrates for dominance of terrestrial ecosystems. The coal swamp environments that supported these giants were themselves extraordinary ecosystems unlike anything that exists today. Vast forests of tree ferns, club mosses, and early seed plants created multi-layered canopies that trapped moisture and heat, generating greenhouse-like conditions across enormous areas. These weren't sparse woodlands with scattered trees. They were dense, jungle-like environments where humidity approached saturation and temperatures remained warm year-round. The plant communities of these ancient forests were dominated by species that have no modern equivalents. Tree ferns reached heights of 40 meters, creating canopies comparable to modern tropical rainforests, but composed entirely of spore-bearing plants. Club mosses grew to the size of large trees, their scale-like leaves creating dense shade that supported an incredible diversity of smaller plants and arthropods. These forests were also remarkably productive, generating enormous amounts of plant material that accumulated faster than it could decompose. The combination of high temperatures, abundant moisture, and rapid plant growth created ideal conditions for coal formation, but it also provided an almost unlimited food supply for detritivorous arthropods like Arthropleura. The aquatic environments of the Carboniferous were equally spectacular. Shallow seas, river deltas, and freshwater swamps teemed with life forms that exploited the oxygen-rich conditions in their own ways. Giant sea scorpions, though not insects, represented another lineage of arthropods that achieved remarkable sizes during this period. These aquatic predators could reach lengths of over 2 meters, creating an arthropod-dominated ecosystem that extended from terrestrial forests into marine environments. The transition zones between terrestrial and aquatic habitats were particularly rich in giant arthropods. These marginal environments provided access to both terrestrial and aquatic food sources, while offering protection from the extreme conditions that sometimes characterize purely terrestrial or marine settings. Many of the most spectacular Carboniferous giants appear to have thrived in these transitional zones, taking advantage of the best of both worlds. Climate played a crucial role in maintaining the conditions that supported these extraordinary creatures. The Carboniferous experienced relatively stable, warm temperatures, with minimal seasonal variation across much of the tropical zone. This climate stability allowed ecosystems to develop and maintain the complex food webs necessary to support large predators and detritivores. The absence of ice caps during much of the Carboniferous meant that sea levels remained high and stable, creating extensive shallow marine and coastal environments that supported diverse arthropod communities. The warm temperatures also enhanced the efficiency of arthropod metabolism, allowing large-bodied species to maintain the high energy demands associated with their massive sizes. But this stable, warm world was not destined to last forever. Even as the giants of the Carboniferous reached their peak diversity and size, forces were already at work that would bring their reign to an end. The very processes that had created their oxygen-rich world were beginning to slow down, setting the stage for dramatic changes that would reshape life on Earth. The geological forces that had sustained the Carboniferous giants for millions of years were subtle at first, operating on timescales that made them invisible to the creatures living through them. The massive coal swamp forests that had pumped oxygen into the atmosphere were gradually changing, not through any single catastrophic event, but through the slow, inexorable process of continental drift and climate shift. As the continents continued their collision course toward Pangaea, the vast lowland areas that had supported those oxygen-producing forests began to rise and drain, and the chemistry of the atmosphere started its slow transformation around 300 million years ago, though the giants barely noticed at first. Oxygen levels that had peaked at 35% began a gradual decline that would continue for tens of millions of years. The change was so slow that individual generations of insects showed no obvious effects, but over geological time, the very foundation of their world was shifting beneath them. During this transition period, something fascinating happened that reveals just how complex the relationship between these creatures and their environment really was. Some of the largest griffinflies actually persisted well into the Permian period, even as oxygen levels dropped significantly below their Carboniferous peaks. Meganeuropsis permiana, with its massive 71-centimeter wingspan, lived in an atmosphere that contained considerably less oxygen than the world that had originally given rise to giant insects. This persistence challenges our simple understanding of what limited insect size during this period. If oxygen availability was the only constraint, these giants should have vanished as soon as atmospheric composition began to change. Instead, they managed to survive for millions of years in increasingly challenging conditions, suggesting that evolution had fine-tuned their physiology to extract maximum efficiency from whatever oxygen was available. The secret lay in their specialized respiratory adaptations that had evolved specifically for life in oxygen-rich conditions. These weren't just scaled-up versions of modern insect breathing systems. They were highly sophisticated networks of tubes and air sacs that could process enormous volumes of gas with remarkable efficiency. As oxygen levels declined, these systems initially provided enough of a buffer to keep the giants alive, though probably at reduced performance levels. But while the atmospheric giants struggled with declining oxygen, a new threat was emerging that would prove far more immediate and devastating. The skies, which had belonged exclusively to arthropods for over 50 million years, were about to gain their first vertebrate inhabitants. The evolution of flying reptiles marked the beginning of the end for the age of giant insects. Though this transition would unfold over millions of years rather than happening overnight, The first pterosaurs appeared during the late Triassic period, roughly 220 million years ago, still far in the future from our Carboniferous giants. But the evolutionary pressure they would eventually create began much earlier, with the development of increasingly sophisticated terrestrial vertebrates that were experimenting with gliding and powered flight. Even primitive attempts at aerial locomotion by early reptiles would have created selective pressure favoring smaller, more maneuverable insects. The physics of aerial combat strongly favored vertebrates once they achieved true powered flight. Birds and pterosaurs could achieve much higher flight speeds than even the most athletic griffin flies, and their vertebrate nervous systems provided faster reaction times and more sophisticated flight control. A giant insect that had once dominated through sheer size and strength suddenly found itself outclassed by smaller, faster, more agile competitors. This aerial arms race fundamentally changed the evolutionary calculus for flying insects. Size, which had been an advantage in a world without flying predators, became a liability when facing vertebrate hunters. Larger insects made easier targets and couldn't match the acceleration and maneuverability of their new competitors. The selective pressure shifted dramatically toward favoring smaller, more agile species that could exploit ecological niches unavailable to larger vertebrates. The transition wasn't immediate or uniform across all environments. In dense forest canopies where vertebrate flight was limited by obstacles, some larger insects managed to persist longer than their open habitat relatives. But even in these refugia, the writing was on the wall. The age of arthropod aerial dominance was drawing to a close, replaced by an era where insects would succeed through diversity, specialization, and exploitation of ecological niches, rather than through raw size and power. On the ground, the terrestrial giants faced their own set of challenges as the Carboniferous world transformed around them. The coal swamp forests that had provided both habitat and food for creatures like Arthropleura were gradually being replaced by different plant communities better adapted to the changing climate. The massive tree ferns and club mosses that had dominated these ecosystems began to give way to early conifers and other seed plants that created very different forest structures. These new plant communities produced different types of leaf litter and organic debris, potentially affecting the food supply for detritivorous giants like Arthropleura. The chemical composition of plant material was changing as new lineages evolved different defensive compounds and structural materials. What had once been an abundant and easily digestible food source was becoming more challenging to process and less nutritious overall. The changing plant communities also altered the physical structure of terrestrial habitats in ways that affected large arthropods. The open, park-like understories of tree fern forests gave way to denser, more complex vegetation that made movement more difficult for massive creatures with dozens of legs. The trackways and burrow systems that had worked well in soft, swampy sediments became less practical in the firmer soils that developed as water tables dropped and drainage improved. Temperature fluctuations, which had been minimal during the stable Carboniferous climate, began to increase as the supercontinent Pangaea took shape. The massive continental landmass created more extreme seasonal variations and greater temperature differences between coastal and interior regions. Large arthropods, with their high surface area to volume ratios, were particularly vulnerable to these temperature swings, which could disrupt their metabolic processes and energy budgets. The formation of Pangaea also led to the development of extensive arid regions in the continental interior, creating barriers to dispersal for moisture-dependent giants. Species that had once enjoyed continuous habitat across vast areas found themselves increasingly isolated in shrinking refugia. This fragmentation made populations more vulnerable to local extinctions and reduced the genetic diversity necessary for adapting to changing conditions. Permian volcanic activity added another layer of environmental stress that the Carboniferous giants had never experienced. Massive eruptions, particularly those associated with the Siberian traps, released enormous quantities of ash, sulfur compounds, and carbon dioxide into the atmosphere. These volcanic events created acid rain, reduced sunlight penetration, and disrupted global climate patterns in ways that put additional stress on already vulnerable ecosystems. The acid rain produced by volcanic emissions was particularly devastating to arthropods, with their calcium carbonate and chitin exoskeletons. The acidic precipitation could directly damage protective armor and make it more difficult for these creatures to maintain the structural integrity necessary for supporting their massive bodies. Smaller arthropods with lower surface area to volume ratios were less affected, giving them another advantage over their giant relatives. Marine environments experienced their own dramatic changes as the Permian period progressed toward its catastrophic conclusion. Ocean chemistry shifted as carbon dioxide levels fluctuated and volcanic emissions altered seawater composition. The shallow marine and coastal environments that had supported diverse arthropod communities began to experience increased acidity and reduced oxygen levels, creating conditions hostile to many of the specialized ecosystems that had flourished during the Carboniferous. Sea level fluctuations associated with climate change and glacial formation eliminated many of the extensive coastal wetlands that had served as nursery habitats for aquatic arthropod larvae. These transitional environments had been crucial for species with complex life cycles that included both aquatic and terrestrial phases. Their loss created a bottleneck that affected entire lineages of arthropods that depended on these marginal habitats for reproduction. The cooling climate also affected the efficiency of arthropod metabolism in ways that disproportionately impacted larger species. Cold-blooded animals with high energy demands are particularly vulnerable to temperature drops that slow their metabolic processes. Giant arthropods that had thrived in the warm, stable conditions of the Carboniferous found themselves struggling to maintain basic biological functions as average temperatures declined. Ice Age conditions that developed during the late Carboniferous and early Permian created additional challenges for creatures adapted to tropical climates. Even temporary glaciation could eliminate populations across vast areas and fragment previously continuous habitats. The giants that had once roamed across entire continents found themselves restricted to increasingly small refugia, where conditions remained suitable for their specialized requirements. The combination of atmospheric, climatic, and ecological changes created a perfect storm of environmental pressures that gradually overwhelmed the adaptive capabilities of Carboniferous giants. These weren't sudden catastrophic events that wiped out entire lineages overnight. Instead, they represented a slow squeeze that gradually eliminated the conditions necessary for supporting creatures of extraordinary size. As we examine the fossil record of this transition period, we see clear evidence of size reduction across multiple arthropod lineages. Species that had once reached massive proportions gradually evolved smaller body sizes over successive generations. This wasn't necessarily driven by direct selection pressure against size, but rather by the simple fact that smaller individuals had higher survival rates in the changing environment. The largest specimens of any given species became increasingly rare in fossil deposits from later time periods, suggesting that extreme gigantism was becoming evolutionarily unsustainable. Environmental conditions that had once favored the largest individuals now worked against them, creating a selective pressure that gradually pulled average body sizes downward across entire ecosystems. Some lineages managed to persist by adopting different ecological strategies that allowed them to survive with smaller body sizes. Others attempted to maintain their large size, but found themselves increasingly restricted to marginal habitats, where conditions still supported gigantism. The most successful groups were those that could rapidly evolve smaller body sizes, while maintaining their ecological roles in modified form. The end Permian mass extinction, which occurred roughly 250 million years ago, delivered the final blow to most remaining lineages of giant arthropods. This catastrophic event, triggered by massive volcanic eruptions in what is now Siberia, eliminated up to 96% of marine species and 70% of terrestrial vertebrate species. The environmental disruption was so severe that even smaller arthropods struggled to survive, making recovery impossible for the few remaining giants. The aftermath of this extinction event created a biological vacuum that would eventually be filled by new groups of organisms better adapted to post-Paleozoic conditions. Dinosaurs would rise to dominate terrestrial ecosystems, while new groups of insects would evolve to exploit ecological niches in ways that emphasize diversity and specialization rather than raw size. The age of arthropod giants had come to an end, but the legacy of their extraordinary reign would continue to influence our understanding of what life can achieve under the right conditions. Modern paleontologists studying these ancient giants continue to uncover new insights into their biology, ecology, and eventual extinction. Advanced imaging techniques allow researchers to examine fossil specimens in unprecedented detail, revealing anatomical features that were previously invisible. Chemical analysis of ancient sediments provides information about atmospheric composition and environmental conditions that helps explain how these creatures lived and why they disappeared. The study of Carboniferous giants also provides valuable insights into the relationship between environmental conditions and evolutionary outcomes. Understanding how atmospheric composition influenced body size evolution helps scientists predict how modern organisms might respond to current environmental changes. The lessons learned from these ancient ecosystems remain relevant as we face our own period of rapid environmental transformation. Perhaps most importantly, the giants of the Carboniferous remind us that the history of life on Earth is full of extraordinary experiments that push the boundaries of what seemed possible. These creatures achieved sizes and capabilities that seem almost mythical by today's standards, yet they were real animals that lived, hunted, reproduced, and died in ecosystems that operated according to the same fundamental principles that govern life today. Their story is ultimately one of both triumph and limitation. For tens of millions of years, they exploited a unique set of environmental conditions to achieve extraordinary success. But their very specialization for those conditions made them vulnerable when the environment changed. The giants of the Carboniferous teach us that even the most successful adaptations are ultimately temporary, subject to the relentless forces of environmental and evolutionary change that continue to shape life on our planet. The traces they left behind in rock formations around the world continue to inspire wonder and scientific inquiry. Every new fossil discovery adds another piece to the puzzle of how these extraordinary creatures lived and died. Their legacy lives on, not just in museum displays and scientific papers, but in our expanding understanding of the incredible diversity and adaptability of life itself. Their fossilized remains tell stories that stretch our imagination to its limits. When paleontologists first uncovered the massive wing impressions of Meganeura in those French coal deposits over a century ago, they struggled to believe what they were seeing. The sheer scale seemed impossible, like discovering the bones of a dragon in your backyard. Yet there they were, preserved in stone with such exquisite detail that every vein and joint could be mapped with precision. The preservation process itself reveals something profound about the world these giants inhabited. Most Carboniferous arthropod fossils weren't created by sudden catastrophic burial. Instead, they represent molted exoskeletons that were gently covered by fine sediments in oxygen-poor environments at the bottom of swamps and lagoons. This tells us that these creatures were so abundant that their cast-off shells regularly accumulated in fossil-forming environments, creating a record of their lives that spans millions of years. What's particularly fascinating is how complete some of these fossils are. Unlike many ancient creatures known only from fragmentary remains, we have remarkably detailed specimens of Carboniferous giants that preserve everything from wing venation patterns to leg spines to compound eye structures. The level of preservation is so extraordinary that researchers can reconstruct not just what these animals looked like, but how they moved, hunted, and interacted with their environment. Recent advances in fossil analysis have revealed details that would have been impossible to detect just decades ago. High-resolution CT scanning allows paleontologists to peer inside fossil specimens without damaging them, revealing internal structures like breathing tubes, muscle attachment points, and even preserved gut contents. These techniques have revolutionized our understanding of how these giants actually functioned as living animals, rather than just impressive museum pieces. One of the most startling discoveries has been evidence of color patterns in some Carboniferous insect fossils. Microscopic analysis of wing scales and body segments has revealed traces of melanin and other pigments that once gave these creatures their living colors. Imagine Meganeura not as the drab brown creature often depicted in reconstructions, but as a brilliantly colored aerial predator with iridescent wings that flashed in the dappled sunlight of ancient forests. The behavioral evidence preserved in fossil trackways provides another window into the daily lives of these giants. Arthropleura trackways don't just show us where these creatures walked. They reveal details about their gait, their speed, their social behavior, and even their interactions with other species. Some trackways show evidence of Arthropleura moving in groups, suggesting these giants may have been more social than their modern millipede relatives. Even more intriguing are the traces that show interactions between different species. Fossil sites have preserved evidence of giant griffinflies landing near Arthropleura trackways, possibly indicating hunting behavior or territorial disputes. These glimpses of ancient behavior patterns help us understand that Carboniferous ecosystems weren't just collections of oversized creatures, but complex communities with intricate predator-prey relationships and competitive interactions. The chemistry preserved in these ancient fossils tells its own story about the world that supported such extraordinary life forms. Isotopic analysis of arthropod exoskeletons reveals information about their diet, metabolism, and the environmental conditions they experienced during their lives. The ratios of different chemical elements provide clues about atmospheric composition, temperature, and humidity levels that help scientists reconstruct the precise environmental conditions that made gigantism possible. Some of the most remarkable insights come from studying the growth patterns preserved in fossil exoskeletons. Like tree rings, arthropod shells contain growth bands that record seasonal changes and environmental fluctuations experienced during the creature's lifetime. These microscopic features reveal that some Carboniferous giants lived for surprisingly long periods, possibly decades in the case of the largest Arthropleura specimens. The fossil record also preserves evidence of the gradual decline of these giants as environmental conditions changed. Later Carboniferous and early Permian deposits show a clear trend towards smaller body sizes across multiple arthropod lineages. This size reduction wasn't uniform or sudden, but occurred gradually over millions of years as environmental pressures slowly shifted the balance against extreme gigantism. Particularly telling are fossil assemblages that show the coexistence of giant and normal-sized arthropods during transitional periods. These mixed communities provide snapshots of ecosystems in flux, where traditional giants were beginning to struggle while smaller, more adaptable species were gaining advantages. The changing ratios of large to small arthropods in successive rock layers tell a story of gradual ecological transformation. Modern experimental approaches have added another dimension to our understanding of these ancient giants. Researchers have constructed physical models of Meganeura wings to test their aerodynamic properties in wind tunnels. The results confirm that these creatures were indeed capable of sophisticated flight, but also reveal the enormous energy costs associated with keeping such massive bodies airborne. Wind tunnel tests using scale models have shown that griffinfly wings were remarkably efficient at generating lift, but required precise control to maintain stability. The wing loading calculations suggest these giants operated near the maximum possible size for powered flight using insect-style wing mechanics. Any larger, and they would have been unable to generate enough lift to stay aloft, even in the dense, oxygen-rich atmosphere of their time. Computer modeling of Arthropleura locomotion has provided similar insights into the mechanical challenges faced by terrestrial giants. Moving a body over 2 meters long with dozens of legs requires sophisticated coordination to avoid tripping over your own appendages. The models suggest that Arthropleura used wave-like patterns of leg movement similar to modern millipedes, but scaled up to handle the mechanical stresses of supporting such enormous mass. These biomechanical studies reveal that Carboniferous giants were operating at the absolute limits of what arthropod body plans could achieve. They weren't just large versions of modern insects, but highly specialized organisms that pushed biological engineering to its breaking point. Every aspect of their anatomy, from respiratory systems to skeletal support structures, was optimized for life at enormous size under very specific environmental conditions. The engineering principles governing these giants continue to inspire modern biomimetic research. Aerospace engineers study griffinfly wing structures to understand how natural systems achieve efficient flight at low speeds. The hierarchical design of arthropod exoskeletons provides insights for developing lightweight, strong materials for human applications. Even the coordination systems that allowed Arthropleura to control dozens of legs simultaneously offer lessons for robotics and autonomous systems. But perhaps the most important lesson from studying these ancient giants is what they reveal about the dynamic relationship between life and environment. The Carboniferous period demonstrates that under the right conditions, evolution can produce outcomes that seem almost impossible by modern standards. The giants weren't freaks or evolutionary mistakes. They were successful adaptations to a world that no longer exists. Their extinction teaches us equally important lessons about the limits of specialization. The very adaptations that made these creatures successful in their oxygen-rich world became liabilities when conditions changed. The respiratory systems that efficiently processed hyperoxic air struggled in lower oxygen environments. The massive body sizes that provided advantages in predator-free skies became disadvantages when facing vertebrate competitors. This pattern of extreme specialization, followed by vulnerability to environmental change, appears repeatedly throughout the fossil record. It's a reminder that evolutionary success is always context-dependent, and that even the most impressive adaptations are ultimately temporary responses to specific environmental conditions. The giants of the Carboniferous achieved extraordinary things within their ecological niche, but their very success made them vulnerable to change. The study of these ancient ecosystems also provides perspective on current environmental changes occurring on our planet. While modern atmospheric conditions are different from those of the Carboniferous, we're experiencing our own period of rapid environmental transformation. Understanding how past ecosystems responded to changing conditions helps scientists predict and prepare for the biological consequences of current environmental shifts. Modern insects, despite their smaller size, represent the evolutionary descendants of Carboniferous lineages that survived the transition to lower oxygen conditions. Their success demonstrates the adaptive value of smaller body sizes and greater ecological flexibility. Today's insects achieve through diversity and specialization what their ancient relatives accomplished through raw size and power. The arthropod respiratory systems that once supported giants now power an incredible array of smaller species that have colonized virtually every terrestrial and freshwater habitat on Earth. The same basic breathing mechanism that allowed Meganeura to fly through Carboniferous skies now enables modern bees to pollinate flowers, enables ants to build complex societies, and enables countless other insects to perform the ecological functions that keep modern ecosystems running. This evolutionary continuity links us directly to that ancient world of giants. Every time we see a dragonfly hovering over a pond or watch a millipede crawling through leaf litter, we're observing the living legacy of Carboniferous gigantism. The basic body plans and physiological systems were established hundreds of millions of years ago, refined through countless generations of evolution and environmental change. The fossil sites that preserve these ancient giants continue to yield new discoveries that expand our understanding of their world. Recent excavations in Carboniferous deposits have uncovered previously unknown species of large arthropods. each adding new pieces to the puzzle of how these ecosystems functioned. Advanced preparation techniques allow paleontologists to extract fossils that would have been impossible to study just years ago. International collaborations between research institutions have created detailed databases of Carboniferous arthropod fossils from sites around the world. These comprehensive datasets reveal global patterns in the distribution and evolution of giant arthropods that weren't apparent when studying individual fossil localities in isolation. The picture that emerges is one of worldwide ecosystems dominated by oversized arthropods operating according to biological principles we're only beginning to understand. Educational programs inspired by these discoveries are introducing new generations of students to the wonders of paleontology and evolutionary biology. Museum exhibits featuring life-sized models of Meganeura and Arthropleura capture public imagination while teaching important lessons about evolution, extinction, and environmental change. These outreach efforts ensure that the scientific legacy of Carboniferous giants extends far beyond academic research. The technological tools used to study these fossils continue to advance, promising even greater insights in the future. New imaging techniques, chemical analysis methods, and computer modeling approaches will undoubtedly reveal aspects of Carboniferous life that remain hidden today. Each technological advance opens new windows into this ancient world, allowing us to see it with ever greater clarity and detail. Perhaps most importantly, the study of Carboniferous giants reminds us that life on Earth has achieved extraordinary diversity and complexity throughout its history. The giants of the Carboniferous represent just one chapter in this ongoing story, but it's a chapter that demonstrates the incredible potential of evolution to produce outcomes that challenge our assumptions about what's possible. Their fossilized remains will continue to inspire wonder and scientific inquiry for generations to come. Each specimen represents an individual organism that lived, breathed, hunted, and died in forests that vanished hundreds of millions of years ago. Yet through the miracle of fossilization and the dedication of paleontologists, these ancient giants continue to teach us about the history of life and our place within it. The giants of the Carboniferous achieved something truly remarkable. They proved that under the right conditions, arthropods could compete directly with vertebrates for dominance of terrestrial and aerial ecosystems. They demonstrated that the limits we perceive in modern biology aren't absolute constraints, but rather reflections of current environmental conditions. Most importantly, they showed us that the history of life is full of extraordinary experiments that expanded the boundaries of what seemed possible. Standing before a fossil of Meganeura or Arthropleura in a museum today, we're not just looking at the remains of extinct animals. We're witnessing evidence of a biological revolution that reshaped our understanding of evolution, ecology, and environmental change. These giants remind us that life has always been more creative, more adaptable, and more extraordinary than we imagine. More adaptable and more extraordinary than we imagine. The mysteries surrounding these ancient titans extend far beyond what we can observe in their fossilized remains. Recent discoveries have revealed that the Carboniferous period wasn't just an era of biological gigantism, but a time when the fundamental rules of ecology were completely rewritten. The relationships between predators and prey, the flow of energy through ecosystems, and even the basic physics of movement and metabolism operated under principles that seem almost alien by today's standards. Consider the energetics of being a giant in the Carboniferous world. Modern physics tells us that maintaining a large body requires exponentially more energy than supporting a smaller one. Yet somehow, creatures like Arthropleura managed to power bodies weighing 50 kilograms through dense forest undergrowth, while Meganeura sustained flight speeds that would challenge modern birds. The mathematics of their existence suggests metabolic efficiencies that pushed biological systems to their absolute limits. The oxygen-rich atmosphere wasn't just beneficial for respiratory function. It fundamentally altered the chemistry of cellular metabolism in ways that we're only beginning to understand. At 35% atmospheric oxygen, biochemical reactions that normally require complex enzyme systems could proceed more efficiently with simpler catalysts. This meant that carboniferous giants could achieve metabolic rates that would be impossible under current atmospheric conditions, effectively overclocking their biological systems. But this metabolic supercharging came with serious risks. High oxygen concentrations don't just enhance beneficial reactions, they also accelerate destructive processes like oxidation and free radical formation. The cellular machinery of these giants had to evolve sophisticated antioxidant systems to prevent their own metabolic processes from literally burning them up from the inside. It was biological life lived on the edge, where the same conditions that enabled extraordinary performance also threatened catastrophic failure. The fossil evidence suggests that some carboniferous arthropods developed remarkable physiological innovations to handle these extreme conditions. Specialized cellular structures, preserved as microscopic traces in exceptionally well-preserved specimens, appear to be enlarged versions of organelles responsible for managing oxygen toxicity. These giants weren't just bigger versions of modern arthropods. They were biochemically distinct organisms adapted for life in an atmosphere that would be lethal to most modern animals. The predatory strategies employed by creatures like Meganeura reveal another layer of complexity in carboniferous ecosystems. Modern dragonflies are already among the most efficient hunters in the animal kingdom, with success rates approaching 95% when pursuing prey. Scaling up this predatory precision to the size of Meganeura suggests hunting capabilities that would have made these aerial giants virtually unstoppable within their size class. Analysis of preserved gut contents in some griffinfly specimens has revealed prey items that seem almost impossible by modern standards. These aerial predators were taking down other flying arthropods with wingspans approaching 30 centimeters, prey animals that would themselves be considered giants today. The biomechanics of such encounters suggest aerial combat scenarios that resemble dogfights between small aircraft more than anything we see in modern insect predation. The compound eyes of these giant predators represent another marvel of biological engineering, scaled to extraordinary proportions. Some preserved eye structures contain over 20,000 individual light-detecting units, each capable of tracking movement across vast distances. The visual processing power required to integrate input from such complex sensory systems suggests neural architectures that approach the computational complexity of simple vertebrate brains. Recent studies using advanced scanning techniques have revealed internal structures within griffinfly heads that appear to be enlarged versions of the ganglia that control flight in modern insects. These neural clusters were proportionally much larger than anything seen in contemporary arthropods, suggesting that the giants had evolved enhanced information processing capabilities to coordinate their complex aerial maneuvers and hunting strategies. The terrestrial giants faced their own unique set of engineering challenges that required equally innovative solutions. Moving a 2.5-meter body with dozens of legs through dense vegetation without becoming tangled requires coordination systems that border on the miraculous. Modern centipedes and millipedes achieve this coordination through relatively simple neural circuits that generate wave-like patterns of leg movement. Scaling this system up to handle 30 or more body segments required neural innovations that we're only beginning to appreciate. Trackway evidence suggests that Arthropleura could modulate its gait patterns depending on terrain and circumstances. In open areas, the creatures appear to have used a relatively simple wave-like pattern similar to modern millipedes. But in dense vegetation or rough terrain, the trackways show evidence of more complex coordination patterns that allowed individual leg segments to adjust their movements independently while maintaining overall forward momentum. This behavioral flexibility suggests neural capabilities that went far beyond simple reflexive responses. These giants appear to have possessed something approaching genuine intelligence, at least within the limited scope of navigating complex three-dimensional environments. The ability to plan movement sequences and adapt to changing conditions on the fly requires cognitive abilities that challenge our assumptions about arthropod mental capabilities. The social aspects of Carboniferous giant behavior remain one of the most intriguing puzzles in paleontology. Several fossil sites preserve evidence of multiple Arthropleura individuals moving through the same areas in what appear to be coordinated patterns. Whether this represents true social behavior or simply convergent responses to environmental factors remains debated, but the possibility that these giants engaged in complex social interactions adds another layer to their already remarkable biology. Even more fascinating are fossil sites that preserve evidence of interspecific interactions between different types of giants. Trackways showing Arthropleura paths intersecting with those of other large arthropods suggest that these ecosystems supported multiple species of giants that somehow partitioned resources and habitat space. The ecological mechanisms that allowed such coexistence remain mysterious, but they point toward community structures of extraordinary complexity. The reproductive biology of these giants presents another set of challenges that required innovative evolutionary solutions. Modern arthropods face significant constraints when scaling up their reproductive systems, as the mechanics of mating and egg-laying become increasingly difficult with larger body sizes. The giants of the Carboniferous must have evolved specialized reproductive strategies that overcame these scaling problems, though direct evidence of such adaptations remains frustratingly elusive in the fossil record. What we do know suggests that some giants may have had extended lifespans that allowed them to invest heavily in growth before reaching reproductive maturity. Growth band analysis of the largest Arthropleura specimens indicates lifespans that may have exceeded several decades, far longer than any modern terrestrial arthropod. This extended development period would have allowed these creatures to reach their massive adult sizes, while still maintaining the energy reserves necessary for reproduction. The juveniles of these giant species present their own fascinating evolutionary story. Recent discoveries of juvenile Arthropleura and griffinfly specimens reveal that these creatures didn't simply scale up from small versions of their adult forms. Instead, they underwent complex developmental transformations that involved significant changes in body proportions, sensory systems, and locomotory mechanisms as they grew. Juvenile Arthropleura, for example, show evidence of more aquatic adaptations than their terrestrial adults, including modified leg structures that may have functioned as swimming appendages. This suggests that the largest terrestrial arthropods of all time actually spent their early lives in aquatic environments, only transitioning to terrestrial habitats as they reached adult size. Such complex life cycles would have required precise coordination between aquatic and terrestrial ecosystem components. The environmental engineering capabilities of these giants extended their influence far beyond their immediate feeding and movement activities. Large burrowing arthropods like Arthropleura were essentially ecosystem engineers, creating underground networks that altered soil chemistry, hydrology, and nutrient cycling across vast areas. Some burrow systems attributed to these creatures extend for hundreds of meters underground, representing construction projects that rival those of modern vertebrate engineers like beavers. These burrow networks didn't just provide shelter for their builders, they created subterranean habitat corridors that were utilized by countless smaller organisms. The ecological impact of this underground engineering may have been as significant as the more visible effects of giant herbivores on plant communities. Entire underground ecosystems appear to have been structured around the burrowing activities of giant arthropods. The chemical signatures preserved in ancient soils provide evidence that giant arthropod activities significantly altered the biogeochemical cycles of Carboniferous ecosystems. The massive amounts of organic matter processed by creatures like Arthropleura created localized zones of enhanced nutrient availability that supported distinctive plant communities. These giants weren't just living in their ecosystems, they were actively reshaping them through their daily activities. As the Carboniferous period progressed toward its end, the fossil record reveals increasingly sophisticated adaptations among the surviving giants. Rather than simply declining in the face of environmental challenges, some lineages evolved enhanced physiological capabilities that allowed them to maintain their large body sizes, even as atmospheric oxygen began its slow decline. These adaptations represent some of the most remarkable examples of evolutionary innovation in response to environmental stress. Advanced respiratory structures preserved in late Carboniferous fossils show evidence of increasingly complex internal air circulation systems. Some specimens display branching patterns in their breathing tubes that approach the efficiency of vertebrate lung systems. These innovations allowed giants to extract more oxygen from each breath, compensating for the gradually declining atmospheric concentrations through improved physiological efficiency. The preservation of soft tissue structures in some exceptional fossil specimens has revealed details about the internal anatomy of these giants that were previously impossible to study. Advanced imaging techniques can now visualize preserved muscle fibers, nervous system components, and even cellular structures within the fossilized remains. These microscopic details provide unprecedented insights into how these creatures actually functioned as living organisms. Perhaps most remarkably, some preserved specimens retain traces of the original biochemical compounds that powered these ancient giants. Molecular paleontology techniques can now extract and analyze organic molecules that have survived for hundreds of millions of years within fossil arthropod exoskeletons. These chemical fossils provide direct evidence about the metabolic processes that supported gigantism during the Carboniferous period. The global distribution of Carboniferous giant fossils reveals patterns that help us understand the environmental conditions necessary for supporting such extraordinary creatures. Giant arthropods weren't randomly distributed across ancient landscapes. Instead, they were concentrated in specific geographic and ecological zones that provided optimal combinations of temperature, humidity, oxygen levels, and food availability. Mapping these fossil distributions against reconstructions of ancient climate and geography shows that giants were most abundant in equatorial regions, where warm, stable conditions persisted throughout the year. The absence of giant arthropod fossils from higher latitude sites suggests that even during the globally warm Carboniferous period, temperature constraints limited the geographic range of these extraordinary creatures. The timing of giant arthropod appearances and extinctions also reveals important patterns about the environmental controls on gigantism. The largest species didn't all appear simultaneously, but instead evolved sequentially as atmospheric oxygen levels rose and stabilized. Similarly, their extinctions weren't synchronous events, but occurred gradually over millions of years as environmental conditions shifted. This temporal pattern suggests that the evolution of gigantism was a dynamic process that responded to changing environmental opportunities and constraints. As conditions became favorable for larger body sizes, multiple arthropod lineages independently evolved giant forms. When conditions shifted against gigantism, these same lineages either evolved smaller body sizes or went extinct, depending on their evolutionary flexibility. The legacy of Carboniferous giants extends far beyond their immediate ecological impact during their time on Earth. The evolutionary innovations they developed to achieve and maintain large body sizes influenced the subsequent evolution of arthropods in ways that persist to this day. Modern arthropod respiratory systems, skeletal structures, and nervous system architectures all bear traces of adaptations first developed by their giant ancestors. Even more significantly, the study of these ancient giants has revolutionized our understanding of the relationship between environmental conditions and evolutionary outcomes. The Carboniferous period demonstrates that life can achieve extraordinary diversity and complexity when environmental conditions permit, but also shows how specialized adaptations can become evolutionary dead ends when those conditions change. The implications extend beyond paleontology into fields ranging from astrobiology to climate science. Understanding how Earth's atmosphere influenced the evolution of life helps scientists predict what kinds of organisms might evolve on planets with different atmospheric compositions. The giants of the Carboniferous provide a window into the biological possibilities that emerge under environmental conditions different from those that prevail today. Modern conservation biology also draws lessons from the study of Carboniferous extinctions. The gradual decline of giant arthropods as environmental conditions changed provides insights into how contemporary species might respond to current environmental shifts. The patterns of survival and extinction during the transition from the Carboniferous to later periods offer guidance for predicting which modern species are most vulnerable to ongoing environmental changes. The technological innovations developed to study these ancient giants continue to advance our capabilities for understanding life in deep time. Every new analytical technique reveals previously hidden aspects of their biology and ecology. As our tools become more sophisticated, the giants of the Carboniferous continue to yield new insights about the history of life and the environmental factors that shape evolutionary outcomes. Perhaps most importantly, these extraordinary creatures remind us that the history of life on Earth is far more dynamic and creative than we often imagine. The giants of the Carboniferous achieved biological solutions to environmental challenges that pushed the boundaries of what seemed possible. Their success demonstrates that evolution can produce outcomes that seem almost miraculous when the right environmental conditions align with sufficient evolutionary time. The fossilized remains of these ancient giants will continue to inspire scientific research and public fascination for generations to come. Each specimen represents not just an individual organism, but a window into an entire world that operated according to biological principles we're still working to understand. Their legacy lives on in every modern arthropod that carries genes descended from those ancient lineages, and in every scientific discovery that expands our appreciation for the extraordinary diversity of life that has existed on our planet. Standing before these fossils today, we're not just observing the remains of extinct animals. We're witnessing evidence of life's incredible ability to innovate and adapt to environmental opportunities. The giants of the Carboniferous proved that when conditions permit, evolution can achieve outcomes that stretch our imagination and challenge our assumptions about the limits of biological possibility. Their story continues to unfold as new discoveries reveal additional details about their remarkable world. Each fossil site excavated, each specimen analyzed, and each research paper published adds another chapter to our understanding of this extraordinary period in Earth's history. The giants may be extinct, but their influence on our understanding of life, evolution, and environmental change remains as profound today as it was when their fossils were first discovered over a century ago. The Carboniferous giants achieved something that no arthropods before or since have accomplished. They proved that under the right conditions, invertebrates could evolve to sizes that allowed them to compete directly with vertebrates for dominance of terrestrial and aerial ecosystems. They demonstrated that the constraints we observe in modern biology aren't absolute limits, but rather reflections of current environmental conditions. Most importantly, they showed us that the history of life is full of extraordinary experiments that expanded the boundaries of what we thought possible. Experiments whose lessons continue to inform our understanding of evolution, ecology, and our own place within the grand story of life on Earth. Story of life on Earth. The mechanics of extinction aren't always dramatic. Sometimes they unfold like a slow-motion catastrophe that takes millions of years to complete. As we follow the fossil record through the late Carboniferous and into the Permian period, we see something remarkable happening to the giants that had dominated Earth's ecosystems for so long. They weren't disappearing overnight in some sudden apocalypse. Instead, they were slowly shrinking, generation by generation, Until the age of arthropod, titans finally faded into evolutionary memory. The first signs of trouble appeared around 290 million years ago, as oxygen levels continued their gradual decline from their Carboniferous peaks. But the giants didn't simply vanish, they adapted. Fossil specimens from this transitional period show increasingly sophisticated respiratory modifications that allowed large arthropods to extract more efficiency from each breath. Internal air sacs became more elaborate. Breathing tube networks developed complex branching patterns that approached the efficiency of vertebrate lung systems. Some lineages managed to maintain impressive sizes, even as atmospheric oxygen dropped to levels that would have been impossible for their earlier ancestors. Meganeuropsis permiana represents the pinnacle of this adaptive strategy. With its 71-centimeter wingspan, this creature lived during the early Permian period, when oxygen levels had already declined significantly from their Carboniferous highs. The fossil specimens show respiratory systems so highly modified that they barely resembled those of earlier griffinflies. These weren't just bigger versions of Carboniferous giants. They were evolutionary marvels that had been fine-tuned to extract maximum performance from increasingly challenging atmospheric conditions. The engineering behind these late-surviving giants reveals the extraordinary plasticity of arthropod physiology. Advanced imaging of Meganeuropsis fossils shows internal structures that bear more resemblance to vertebrate respiratory systems than to those of typical insects. Enlarged air sacs, modified breathing tubes, and specialized gas exchange surfaces allowed these creatures to process oxygen with remarkable efficiency. They were living proof that evolution could find solutions to seemingly impossible physiological challenges. But even the most sophisticated adaptations have their limits. As atmospheric conditions continue to deteriorate, the energy costs of maintaining giant body sizes began to outweigh the benefits. The fossil record from the Middle Permian shows a clear trend towards smaller average body sizes across multiple arthropod lineages. The giants were being squeezed out of existence by the relentless mathematics of metabolic economics. The story becomes more complex when we consider the ecological pressures that were simultaneously building against these magnificent creatures. The first flying vertebrates were still millions of years in the future, but early gliding reptiles were already experimenting with aerial locomotion. Even primitive attempts at powered flight created new selective pressures that favored smaller, more maneuverable arthropods over their massive relatives. Ground-dwelling vertebrates were also becoming more sophisticated predators during this transitional period. Early synapsids, the ancestors of modern mammals, were developing increasingly effective hunting strategies and larger body sizes. Some of these terrestrial predators were beginning to reach sizes that allowed them to threaten even the largest arthropods. The days when size alone provided protection were coming to an end. Climate change added another layer of stress to ecosystems already struggling with declining oxygen levels. The formation of the supercontinent Pangaea was creating more extreme weather patterns and greater seasonal temperature variations. The warm, stable conditions that had characterized the Carboniferous were giving way to a more variable and challenging climate regime. Ice ages became more frequent and severe during the late Carboniferous and early Permian periods. Even temporary glaciation could eliminate giant arthropod populations across vast areas, fragmenting previously continuous habitats into isolated refugia. Species that had once enjoyed ranges spanning entire continents found themselves restricted to increasingly small pockets of suitable habitat. The coal swamp forests that had supported so much of the Carboniferous ecosystem were gradually being replaced by different plant communities, better adapted to drier, more variable conditions. Tree ferns and giant club mosses gave way to early conifers and seed plants that created very different forest structures. The abundant, easily digestible plant debris that had supported creatures like Arthropleura was becoming scarcer and less nutritious. Volcanic activity associated with the formation of Pangaea created additional environmental stresses that pushed already vulnerable ecosystems toward their breaking points. Massive eruptions released sulfur compounds and ash into the atmosphere, creating acid rain that was particularly damaging to arthropods with their calcium-based exoskeletons. The chemical composition of rainwater became increasingly hostile to creatures that had evolved in more benign conditions. Ocean chemistry was also changing in ways that affected the aquatic phases of arthropod life cycles. Many giant species had complex developmental patterns that included aquatic larval stages requiring specific water chemistry conditions. As seawater became more acidic and less oxygenated, these critical nursery habitats began to disappear. The cumulative effect of these environmental changes was a slow but inexorable squeeze on the conditions necessary for supporting giant arthropods. Individual species didn't go extinct suddenly. Instead, they gradually lost their ability to reproduce successfully as environmental conditions moved outside their tolerance ranges. Population sizes declined, genetic diversity was lost, and eventually entire lineages crossed the threshold into extinction. Some giants managed to persist longer than others by retreating into increasingly marginal habitats where conditions remained favorable. Deep forest refugia, protected coastal areas, and isolated wetlands provided temporary sanctuaries for species that could no longer survive in mainstream ecosystems. But these refugia were vulnerable to local disturbances and couldn't support the large populations necessary for long-term evolutionary survival. The fossil record preserves poignant evidence of these final populations struggling to maintain their foothold in a changing world. Late Permian deposits contain specimens of giant arthropods with signs of physiological stress, malformed exoskeletons, and reduced body sizes that suggest populations under severe environmental pressure. These weren't healthy, thriving communities, but rather the last remnants of once dominant lineages fighting a losing battle against environmental change. Reproductive success appears to have been one of the first casualties of environmental deterioration. Giant arthropods, with their extended development times and high energy requirements for reproduction, were particularly vulnerable to any disruption in the environmental conditions necessary for successful breeding. Even minor changes in temperature, humidity, or food availability could prevent successful completion of their complex life cycles. The social behaviors that may have helped some giants survive in groups became liabilities as population densities declined. Trackway evidence suggests that some late surviving Arthropleura populations maintained group movements even as overall numbers dwindled. But these social aggregations may have actually accelerated extinction. By concentrating individuals in areas where local environmental disasters could eliminate entire populations at once. Genetic bottlenecks became increasingly severe as giant populations fragmented and declined. Small, isolated populations lost the genetic diversity necessary for adapting to changing conditions. Inbreeding depression reduced fitness and reproductive success, creating downward spirals that accelerated the path toward extinction. The end Permian mass extinction, occurring roughly 250 million years ago, delivered the final blow to most remaining lineages of giant arthropods. This catastrophic event, triggered by massive volcanic eruptions in what is now Siberia, created environmental conditions so extreme that even smaller, more adaptable species struggled to survive. The few giant arthropods that had managed to persist until this point were eliminated along with 96% of marine species and 70% of terrestrial vertebrates. The volcanic eruptions that caused the end Permian extinction released enormous quantities of carbon dioxide, sulfur compounds, and toxic gases into the atmosphere. Global temperatures rose dramatically, ocean chemistry shifted toward extreme acidity, and vast areas of land became uninhabitable. The environmental disruption was so severe that it took millions of years for ecosystems to recover even basic functionality. In the aftermath of this biological catastrophe, the ecological niches that had once been occupied by giant arthropods remained empty for millions of years. The environmental conditions that had made gigantism possible were gone, replaced by a world where smaller, more adaptable organisms held distinct advantages. When arthropod diversity finally began to recover during the Triassic period, it followed very different evolutionary pathways that emphasized specialization and ecological efficiency rather than raw size. The dinosaurs that would eventually come to dominate terrestrial ecosystems represented a fundamentally different approach to achieving large body size. Unlike arthropods, with their external skeletons and passive respiratory systems, dinosaurs developed internal skeletons and active breathing mechanisms that could be more easily scaled up without hitting the physiological constraints that had limited arthropod gigantism. Birds, which evolved from dinosaur ancestors, would eventually reclaim the skies that had once belonged to giant griffinflies. But these vertebrate flyers achieved aerial mastery through very different anatomical innovations. Active flight muscles, sophisticated nervous systems, and warm-blooded metabolism gave birds capabilities that even the most impressive arthropod giants had never possessed. Modern arthropods represent the evolutionary descendants of smaller Carboniferous lineages that survived the transition to post-Paleozoic conditions. Their success demonstrates that evolutionary survival often favors flexibility over specialization, adaptability over optimization for specific conditions. Today's insects achieve, through diversity and ecological specialization, what their ancient relatives accomplished through impressive size. The respiratory systems that once powered giants now support an incredible array of smaller species that have colonized virtually every terrestrial and freshwater habitat on Earth. The same basic breathing mechanism that allowed Meganeura to patrol Carboniferous skies now enables modern dragonflies to hunt over ponds, allows bees to pollinate flowers, and powers the countless other arthropods that perform essential ecological functions in contemporary ecosystems. Modern millipedes, the closest living relatives of Arthropleura, demonstrate how the basic body plan of these ancient giants has been preserved while being scaled down to more sustainable sizes. The largest contemporary millipedes reach lengths of about 30 centimeters, impressive by modern standards, but tiny compared to their 2.5-meter ancestors. Yet they retain the same basic locomotory patterns, feeding strategies, and ecological roles that characterize their giant relatives. The study of modern arthropod physiology provides insights into the constraints that ultimately limited the size of their ancient relatives. Researchers working with contemporary insects in oxygen-enriched environments have demonstrated that respiratory efficiency does indeed improve at higher oxygen concentrations, supporting the hypothesis that atmospheric composition was crucial for Carboniferous gigantism. But these experiments also reveal that there are absolute limits to how much scaling up is possible even under optimal conditions. Biomechanical studies of living arthropods help explain why giants couldn't persist as environmental conditions changed. The engineering principles governing exoskeleton strength, joint flexibility, and muscle leverage create scaling constraints that become increasingly severe as body size increases. Modern arthropods operate well within these constraints, but Carboniferous giants were pushing against the absolute limits of what their body plans could achieve. The fossil sites that preserve evidence of these ancient giants continue to yield new discoveries that expand our understanding of their biology and extinction. Recent excavations have uncovered previously unknown species of large arthropods that survived later into the Permian period than previously thought. These discoveries suggest that the decline of gigantism was even more gradual and complex than originally realized. Advanced analytical techniques applied to existing fossil collections are also revealing new details about the final phases of giant arthropod evolution. Chemical analysis of late Permian specimens shows evidence of physiological stress and nutritional deficiencies that provide direct evidence of the environmental pressures that drove these lineages to extinction. International databases of arthropod fossils are allowing researchers to track the global patterns of gigantism and extinction with unprecedented precision, The data reveal that different regions experienced the decline of giant arthropods at different times, reflecting local environmental conditions and the complex interactions between climate change, atmospheric composition, and ecological factors. Educational initiatives inspired by these discoveries are helping new generations understand the dynamic nature of evolution and extinction. Museum exhibits featuring the giants of the Carboniferous provide powerful examples of how environmental change can drive evolutionary innovation and, ultimately, extinction. These displays help visitors appreciate both the creativity of evolution and the vulnerability of specialized organisms to environmental change. The technological tools used to study these extinct giants continue to advance, promising even greater insights in the future. New imaging techniques can reveal previously invisible details of fossil anatomy. Improved chemical analysis methods can extract more information from trace compounds preserved in ancient specimens. Advanced computer modeling can test hypotheses about giant arthropod biology and extinction that would be impossible to evaluate through fossil evidence alone. Perhaps most importantly, the study of Carboniferous giants and their extinction provides crucial insights for understanding contemporary environmental challenges. The gradual decline of these magnificent creatures as atmospheric and climatic conditions changed offers a powerful example of how environmental shifts can affect entire ecosystems over geological timescales. The patterns of survival and extinction during the transition from the Carboniferous to later periods provide guidance for predicting how modern species might respond to current environmental changes. Species with high specialization for specific environmental conditions, like the Carboniferous giants, appear to be most vulnerable to environmental shifts. Those with greater ecological flexibility and broader tolerance ranges are more likely to persist through periods of change. Modern conservation efforts draw important lessons from the extinction of Carboniferous giants. The gradual nature of their decline demonstrates that extinctions don't always announce themselves with obvious warning signs. Species can appear stable while actually being on trajectories toward extinction that won't become apparent until it's too late for effective intervention. The role of habitat fragmentation in the decline of giant arthropods also provides insights relevant to contemporary conservation challenges. As suitable habitat became increasingly patchy during the late Carboniferous and Permian periods, giant arthropod populations became more vulnerable to local disasters and genetic bottlenecks. Modern species facing similar habitat fragmentation may be at greater risk than their current population sizes suggest. Climate change lessons from the Carboniferous extinction are particularly relevant today. The giants couldn't adapt quickly enough to keep pace with environmental changes that, while gradual by human standards, were rapid in evolutionary terms. This highlights the importance of maintaining genetic diversity and habitat connectivity to give modern species the best possible chances of adapting to ongoing environmental shifts. The end of the giants marked the close of one of the most extraordinary chapters in the history of life on Earth. For over 50 million years, arthropods had achieved sizes and capabilities that challenged our assumptions about the limits of invertebrate biology. They had colonized aerial and terrestrial environments with a dominance that wouldn't be matched by vertebrates until millions of years later. Their extinction wasn't a failure, but rather the natural consequence of evolutionary specialization for conditions that couldn't persist forever. The same environmental factors that had enabled their extraordinary success eventually became the forces that drove them to extinction. It's a pattern that appears repeatedly throughout the fossil record, reminding us that evolutionary success is always temporary and context-dependent. The legacy of these giants lives on in multiple ways. Their fossilized remains continue to inspire scientific research and public fascination. The evolutionary innovations they developed influence the subsequent evolution of arthropods in ways that persist in modern species. Most importantly, their story provides crucial insights into the relationship between environmental conditions and evolutionary outcomes. that remain relevant for understanding life in our rapidly changing modern world. Standing before their fossils today, we're witnessing more than just the remains of extinct animals. We're observing evidence of life's incredible ability to innovate and adapt when environmental opportunities arise, as well as the ultimate constraints that limit even the most remarkable evolutionary achievements. The giants of the Carboniferous proved that evolution can produce outcomes that seem almost miraculous, but they also demonstrated that even the most spectacular adaptations are ultimately subject to the changing conditions that drive the endless dance of evolution and extinction on our dynamic planet. Their story reminds us that we live in just one moment in the long history of life on Earth, a moment when particular environmental conditions support particular kinds of organisms. The giants show us what was possible when conditions were different, and their extinction teaches us about the forces that will continue to shape life long after our own species has passed into the fossil record. In their rise and fall, we see reflected the entire drama of evolution itself, the endless creativity of life balanced against the relentless pressure of environmental change that ensures that nothing, no matter how magnificent, lasts forever, lasts forever. In the quiet halls of paleontology museums around the world, visitors often pause before displays of Carboniferous giants with a mixture of awe and disbelief. These fossilized remains challenge our fundamental understanding of what life can achieve, forcing us to confront the reality that Earth once operated according to biological rules that seem almost mythical by today's standards. The preservation quality of these specimens is so extraordinary that researchers can examine details down to individual muscle attachment points and wing vein patterns, creating windows into a world that vanished hundreds of millions of years ago. Recent advances in fossil preparation techniques have revolutionized how scientists study these ancient giants. Micro-CT scanning allows paleontologists to peer inside specimens without damaging them, revealing internal structures that were previously invisible. Chemical analysis of fossil matrices can detect trace compounds that provide information about diet, metabolism, and environmental conditions. Some specimens preserve such fine details that researchers can identify cellular structures and even traces of original pigments that once gave these creatures their living colors. The distribution of Carboniferous giant fossils across different continents tells a compelling story about the global nature of this evolutionary experiment. From the coal fields of Europe to the fossil beds of North America, similar patterns of gigantism emerged independently in different arthropod lineages. This worldwide phenomenon suggests that the environmental conditions promoting large body sizes were truly global, not just local anomalies in specific ecosystems. Paleontologists working in Carboniferous deposits have developed sophisticated techniques for reconstructing ancient ecosystems based on fossil assemblages. By analyzing the relative abundance of different species, their size distributions, and their preserved behaviors, researchers can piece together food webs and ecological relationships that operated 300 million years ago. These reconstructions reveal ecosystems of extraordinary complexity, where giants interacted with smaller organisms in intricate networks of predation, competition, and cooperation. The process of fossilization itself provides crucial insights into how these giants lived and died. Most arthropod fossils from this period represent molted exoskeletons rather than actual carcasses, indicating that these creatures were abundant enough for their shed shells to accumulate regularly in fossil-forming environments. The exceptional preservation of some specimens suggests rapid burial in oxygen-poor sediments that prevented decay and allowed fine anatomical details to be preserved for hundreds of millions of years. Trace fossils associated with giant arthropods offer another window into their daily lives and behaviors. Massive trackways preserve evidence of how these creatures moved through their environments, revealing gait patterns, travel speeds, and even social behaviors. Some trackway sites show evidence of multiple individuals moving together, suggesting that at least some giants engaged in group behaviors that went beyond simple aggregation around food sources. The burrow systems attributed to creatures like Arthropleura represent some of the most impressive engineering projects in the invertebrate fossil record. These underground networks extended for hundreds of meters and included chambers large enough for the massive arthropods to turn around comfortably. The construction of such extensive burrow systems required sophisticated spatial navigation abilities and long-term planning that challenges our assumptions about arthropod cognitive capabilities. Modern experimental approaches have added new dimensions to our understanding of these ancient ecosystems. Researchers have constructed wind tunnel models to test the aerodynamic properties of giant arthropod wings, confirming that these creatures were indeed capable of powered flight, despite their enormous size. Computer simulations of Arthropleura locomotion have revealed the sophisticated coordination required to move dozens of legs without tangling, demonstrating the remarkable neural control systems these giants must have possessed. The chemistry preserved in ancient soils provides direct evidence of how giant arthropods influence their environments through their daily activities. Isotopic signatures in carboniferous sediments show elevated levels of nitrogen and phosphorus in areas where large arthropods were abundant, indicating that these creatures significantly altered nutrient cycling through their feeding and waste production. Some soil layers preserve chemical traces that can be directly attributed to the burrowing activities of giant millipedes. Biomolecular paleontology has begun to extract actual organic compounds from carboniferous arthropod fossils, providing unprecedented insights into their biochemistry and physiology. Traces of chitin, proteins, and even lipids have been recovered from specimens hundreds of millions of years old. These molecular fossils offer direct evidence about the metabolic processes that supported gigantism and how they differed from those of modern arthropods. The global climate during the Carboniferous period created conditions that were uniquely favorable for arthropod gigantism. Atmospheric models based on geological evidence indicate that not only was oxygen more abundant, but carbon dioxide levels were also significantly different from today's atmosphere. The greenhouse conditions created by this atmospheric composition maintained warm, stable temperatures across much of the planet, eliminating the seasonal stress that limits arthropod activity in modern temperate regions. Ocean chemistry during the Carboniferous was equally distinctive, with higher oxygen levels extending into marine environments and creating conditions that supported diverse communities of aquatic arthropod larvae. Many giant terrestrial species had aquatic juvenile stages that required specific water chemistry conditions for successful development. The loss of these specialized marine nursery habitats, as ocean chemistry changed, may have been one of the factors that ultimately drove giant arthropods toward extinction. The plant communities that dominated Carboniferous landscapes were unlike anything that exists today, creating ecological opportunities that modern arthropods cannot exploit. Giant lycopsids and tree ferns produced massive quantities of organic debris that accumulated in swampy environments, providing an almost unlimited food source for detritivorous arthropods. The chemical composition of this plant material was also different from modern vegetation, lacking many of the defensive compounds that make contemporary plant matter more difficult to digest. Seasonal patterns in Carboniferous ecosystems were minimal compared to modern temperate environments, allowing arthropod activity to continue year-round without the metabolic stress of surviving cold periods. This constant activity enabled giant arthropods to maintain the high energy demands associated with their large body sizes, while also supporting the extended growth periods necessary to reach adult proportions. The absence of large vertebrate predators during the Carboniferous created an ecological vacuum that arthropods were uniquely positioned to fill. Without competition from dinosaurs, mammals, or large reptiles, arthropods could exploit size-based ecological strategies that would later become unavailable once vertebrates evolved to fill similar niches. This predator-free environment lasted for tens of millions of years, providing ample time for arthropods to evolve increasingly sophisticated adaptations for life at large body sizes. Social behaviors among Carboniferous giants remain one of the most intriguing aspects of their biology. Trackway evidence suggests that some species engaged in coordinated movements that went beyond simple aggregation around food sources. Whether these behaviors represented true cooperation or simply convergent responses to environmental cues remains debated, but they indicate levels of behavioral complexity that challenge traditional views of arthropod intelligence. The reproductive strategies of giant arthropods must have been significantly different from those of their modern relatives. Extended lifespans inferred from growth band analysis suggest that these creatures invested heavily in growth before reaching sexual maturity, a strategy that allowed them to achieve their massive adult sizes but also made them vulnerable to environmental changes that could disrupt their extended developmental periods. Physiological innovations that allowed giants to function at their enormous sizes included sophisticated modifications to basic arthropod body plans. Advanced imaging of fossil specimens has revealed internal structures that bear little resemblance to those of modern arthropods, suggesting that gigantism required fundamental reorganization of respiratory, circulatory, and nervous systems. These innovations represent some of the most remarkable examples of evolutionary engineering in the arthropod fossil record. The thermal biology of Carboniferous giants presents another fascinating aspect of their adaptation to ancient conditions. Large body sizes would have provided thermal inertia that helped maintain stable internal temperatures in the warm, humid conditions of their time. This thermal stability may have been crucial for supporting the complex biochemical processes necessary for maintaining such massive bodies, but it also would have made these creatures vulnerable to the temperature fluctuations that accompanied later climate changes. Ecological interactions between different species of giants reveal the complexity of Carboniferous ecosystems. Fossil sites preserve evidence of multiple large arthropod species coexisting in the same environments, suggesting sophisticated mechanisms for resource partitioning and niche segregation. The success of these ecological arrangements demonstrates that gigantism was not simply a matter of individual species achieving large size, but rather a system-level property of entire ecosystems. The geographic distribution of giant arthropod fossils reveals important patterns about the environmental requirements for supporting such extraordinary creatures. Giants were most abundant in equatorial regions where warm, stable conditions persisted throughout the year, while fossil evidence from higher latitudes suggests that even during the globally warm Carboniferous period, temperature constraints limited the distribution of the largest species. Developmental biology inferred from juvenile fossil specimens shows that giant arthropods underwent complex ontogenetic changes as they grew to adult size. Juvenile Arthropleura specimens show anatomical features that differ significantly from adults, suggesting that these creatures occupied different ecological niches during different life stages. This ontogenetic niche shifting may have been crucial for reducing competition between juveniles and adults while allowing populations to exploit a broader range of resources. The engineering constraints that ultimately limited arthropod gigantism become apparent when comparing Carboniferous giants to the theoretical maximum sizes possible for arthropod body plans. Biomechanical analysis suggests that the largest specimens were operating very close to the absolute limits of what external skeletons and passive respiratory systems could support. Any further increase in size would have required fundamental changes to basic arthropod anatomy. Extinction patterns among Carboniferous giants reveal important insights about the relationship between specialization and evolutionary survival. The species that achieved the largest sizes and most extreme adaptations were often the first to disappear as environmental conditions changed, while more generalized forms persisted longer into the Permian period. This pattern suggests that extreme specialization, while allowing remarkable evolutionary achievements, also creates vulnerability to environmental change. The legacy of Carboniferous giants extends far beyond their immediate ecological impact during their time on Earth. The evolutionary innovations they developed influenced the subsequent evolution of arthropods in ways that can still be detected in modern species. Respiratory modifications, skeletal reinforcements, and nervous system enhancements first developed by giants provided the foundation for later arthropod evolution even after gigantism itself was no longer feasible. Modern arthropod diversity represents the evolutionary descendants of smaller Carboniferous lineages that survived the transition to post-Paleozoic conditions. The extraordinary diversity of contemporary insects, with over 1 million described species, demonstrates how evolutionary success can be achieved through specialization and ecological diversification rather than raw size. Today's arthropods accomplish through diversity what their ancient relatives achieved through impressive individual size. The study of Carboniferous giants continues to yield new insights as analytical techniques become more sophisticated and new fossil discoveries expand our understanding of their world. Each new specimen and each technological advance reveals previously hidden aspects of their biology, ecology, and extinction. These discoveries ensure that our understanding of this extraordinary period in Earth's history continues to evolve and deepen. Climate science draws important lessons from the environmental conditions that supported Carboniferous gigantism. Understanding how atmospheric composition influenced biological evolution helps researchers predict how current environmental changes might affect contemporary ecosystems. The giants provide a natural experiment in how life responds to atmospheric conditions very different from those that prevail today. Astrobiology research also benefits from studying these ancient ecosystems as examples of how life might evolve under atmospheric conditions different from those of modern Earth. The relationship between oxygen levels and body size evolution demonstrated by Carboniferous giants provides insights into the kinds of organisms that might evolve on planets with different atmospheric compositions. Conservation biology draws crucial lessons from the patterns of survival and extinction that characterize the end of the Carboniferous period. The gradual decline of giant arthropods as environmental conditions changed provides a powerful example of how specialized organisms can be vulnerable to environmental shifts that occur over timescales much longer than individual lifespans. Educational programs inspired by these discoveries help new generations appreciate both the creativity of evolution and the dynamic nature of life on Earth. Museum exhibits featuring life-sized models of Carboniferous giants provide tangible connections to deep time while illustrating important principles about evolution, ecology, and environmental change. The technological innovations developed to study these fossils continue to advance our capabilities for understanding ancient life. New imaging techniques, chemical analysis methods, and computer modeling approaches promise to reveal even more about these extraordinary creatures in the future. Each advance opens new windows into their world and expands our appreciation for the complexity of ancient ecosystems. Perhaps most importantly, the giants of the Carboniferous remind us that life on Earth has achieved remarkable diversity and complexity throughout its history. Their existence demonstrates that evolution can produce outcomes that stretch our imagination and challenge our assumptions about biological limits. Their extinction teaches us about the temporary nature of even the most impressive evolutionary achievements. The fossilized remains of these ancient giants will continue to inspire scientific research and public fascination for generations to come. Each specimen represents not just an extinct organism, but a window into an entire world that operated according to principles we're still working to understand. Their legacy lives on in every modern arthropod and in every scientific discovery that expands our understanding of life's extraordinary potential. Standing before these fossils today, we're witnessing evidence of one of evolution's most ambitious experiments. The giants of the Carboniferous proved that when environmental conditions align with evolutionary opportunity, life can achieve outcomes that seem almost impossible by contemporary standards. Their story continues to unfold as new discoveries reveal additional details about their remarkable world, ensuring that these ancient titans remain as relevant to our understanding of life today as they were when their fossils were first discovered. The giants achieved something truly extraordinary during their reign on ancient Earth. They demonstrated that arthropods could evolve to sizes that allowed them to dominate ecosystems in ways that seem almost mythical today. They proved that the limits we observe in modern biology aren't absolute constraints, but rather reflections of current environmental conditions. Most significantly, they showed us that the history of life is filled with remarkable experiments that expanded the boundaries of what seemed possible. Experiments whose lessons continue to inform our understanding of evolution, extinction, and the endless creativity of life itself. Creativity of life itself. The mathematics of being giant in a changing world tell a story that's both beautiful and heartbreaking. As we trace the fossil record through those final million years of the Permian period, we see something remarkable happening to the creatures that had once ruled Earth with such magnificent authority. They weren't just disappearing, they were transforming, shrinking, adapting in ways that reveal the extraordinary plasticity of life even in its darkest hours. Picture the last populations of Meganeuropsis struggling to maintain their aerial territories as atmospheric oxygen dropped below 28%. These weren't the effortless aerial predators of earlier eras. Fossil evidence suggests they had to work harder for every wing beat, their massive bodies requiring increasingly sophisticated respiratory modifications just to stay aloft. Some specimens show enlarged air sacs that approach the complexity of vertebrate lung systems, evolutionary innovations that bought them time in a world that was slowly suffocating their way of life. The trackways left by late surviving Arthropleura tell an even more poignant story. These final giants weren't the confident ecosystem engineers of their Carboniferous heyday. Their paths show hesitation, shorter distances between rest stops, evidence of populations struggling to find suitable habitat in landscapes that had become increasingly hostile to creatures of their size. Some trackways end abruptly at what appear to be dried lake beds or degraded soil conditions, suggesting individual animals that simply couldn't find the environmental conditions necessary to continue their journeys. But extinction rarely announces itself with dramatic flourishes. More often, it whispers through the fossil record in subtle changes that only become apparent when viewed across vast spans of time. The giants didn't vanish overnight in some apocalyptic catastrophe. Instead, they faded gradually, their populations declining generation by generation as the world transformed around them. The chemistry preserved in late Permian sediments reveals atmospheric oxygen levels dropping toward 23%. Still higher than today's atmosphere, but far below the hyperoxic conditions that had originally enabled gigantism. For creatures whose entire physiology had been optimized for processing oxygen-rich air, this decline created metabolic stress that compounded with every other environmental challenge they faced. Temperature fluctuations became more severe as the supercontinent Pangaea reached its final configuration. The massive landmass created continental climate patterns with extreme seasonal variations that challenged creatures adapted to the stable warmth of earlier periods. Fossil evidence suggests that some late surviving giants attempted to cope by developing more sophisticated behavioral thermoregulation, seeking shelter in caves and burrows during extreme weather events. The plant communities that had sustained terrestrial giants for millions of years were undergoing their own dramatic transformations. Coal swamp forests gave way to more open woodland dominated by early conifers and seed plants. The abundant, easily digestible organic matter that had supported creatures like Arthropleura became scarcer and more difficult to process. Chemical analysis of preserved gut contents shows evidence of nutritional stress in late Permian specimens. Volcanic activity associated with the Siberian traps began affecting global climate patterns even before the final mass extinction event. Ashfalls and acid rain created additional stress for arthropods, whose exoskeletons were vulnerable to chemical damage. Some fossil specimens from this period show evidence of abnormal growth patterns and shell deformities that suggest environmental toxicity. The first signs of vertebrate competition were also beginning to appear. While true flying vertebrates were still millions of years in the future, early archosaurs were developing increasingly sophisticated terrestrial hunting strategies. Some of these predators were reaching sizes that allowed them to threaten even large arthropods. The ecological advantages that had once made size beneficial were gradually being eroded by changing competitive landscapes. Marine environments were experiencing their own dramatic changes that affected arthropods with aquatic larval stages. Ocean acidification and declining oxygen levels in seawater created challenging conditions for juvenile development. Many coastal wetlands that had served as nursery habitats were being eliminated by sea level fluctuations and changing drainage patterns. The social behaviors that may have helped some giants survive in groups became increasingly difficult to maintain as population densities declined. Trackway evidence suggests that some late-surviving Arthropleura populations maintained coordinated movements even as overall numbers dwindled. But these aggregations may have actually increased vulnerability by concentrating individuals in areas where local disasters could eliminate entire populations. Genetic diversity was being lost as populations became increasingly fragmented and isolated. Small populations in marginal habitats faced inbreeding depression that reduced fitness and reproductive success. The genetic bottlenecks created downward spirals that accelerated extinction trajectories even for populations that appeared stable in the short term. Reproductive success appears to have been one of the first casualties of environmental deterioration. Giant arthropods, with their extended development times and high energy requirements, were particularly vulnerable to any disruption in breeding conditions. Even minor changes in temperature or humidity could prevent successful completion of their complex life cycles. The timing of these various stresses created cascading effects that overwhelmed the adaptive capabilities of even the most resilient giant species. Climate change affected plant communities, which altered food availability, which reduced reproductive success, which decreased population sizes, which increased vulnerability to additional stresses. The interconnected nature of these challenges made recovery increasingly unlikely. Some lineages attempted to adapt by evolving smaller body sizes that required less energy and were more tolerant of environmental stress. Fossil evidence shows clear trends towards size reduction in multiple arthropod groups during the late Permian. But these evolutionary responses required time that many populations simply didn't have as environmental conditions deteriorated rapidly. The fossil record preserves evidence of desperate adaptations as giants struggled to survive in increasingly challenging conditions. Some specimens show respiratory modifications so extreme that they barely resembled their ancestral forms. Others developed behavioral strategies like extended dormancy periods that allowed them to wait out unfavorable conditions, but these adaptations often came with trade-offs that reduced overall fitness. The end Permian mass extinction delivered the final blow to ecosystems already under severe stress. The massive volcanic eruptions that triggered this catastrophe released quantities of carbon dioxide, sulfur compounds, and toxic gases that created environmental conditions incompatible with complex life. Global temperatures rose by 10 to 15 degrees Celsius. Ocean chemistry shifted toward extreme acidity. Vast areas of land became uninhabitable. The environmental disruption was so severe that it eliminated not just the remaining giants, but also most of the smaller organisms that might have served as evolutionary stepping stones for recovery. Entire ecosystems collapsed, leaving biological vacuums that would take millions of years to refill. The conditions that had made arthropod gigantism possible were not just temporarily disrupted, but fundamentally altered. In the aftermath of this biological catastrophe, The world that emerged was fundamentally different from the one that had supported Carboniferous giants. Atmospheric oxygen levels stabilized at lower concentrations that favored different evolutionary strategies. Climate patterns became more variable and seasonal. Plant communities developed new chemical defenses that made organic matter more difficult to process. The dinosaurs that would eventually rise to dominate terrestrial ecosystems represented a completely different approach to achieving large body size. Their internal skeletons and active respiratory systems could be scaled up more effectively than arthropod body plans. Their warm-blooded metabolism provided advantages in variable climate conditions. Their sophisticated nervous systems allowed complex behaviors that arthropods couldn't match. When arthropod diversity finally began to recover during the Triassic period, it followed evolutionary pathways that emphasized specialization and efficiency rather than raw size. Modern insects achieved their ecological success through incredible diversity, sophisticated social behaviors, and exploitation of specialized niches rather than through dominance based on large body size. The respiratory systems that once powered giants now support over 1 million described species of insects that have colonized virtually every terrestrial and freshwater habitat on Earth. The same basic breathing mechanism that allowed Meganeura to hunt in Carboniferous skies now enables modern bees to pollinate flowers, allows ants to build complex societies, and powers countless other arthropods that perform essential ecological functions. Modern millipedes demonstrate how the basic body plan of terrestrial giants has been preserved while being scaled down to sustainable sizes. Contemporary species reach maximum lengths of about 30 centimeters, impressive by current standards, but tiny compared to their 2.5-meter ancestors. Yet they retain the same fundamental locomotory patterns, feeding strategies, and ecological roles. The study of modern arthropod physiology in oxygen-enriched laboratory conditions has confirmed that respiratory efficiency does improve at higher oxygen concentrations, supporting the atmospheric hypothesis for Carboniferous gigantism. But these experiments also reveal absolute limits to scaling that explain why giants couldn't persist as environmental conditions changed. Biomechanical analysis of living arthropods helps explain the engineering constraints that ultimately doomed the giants. The mathematics of structural support, joint mechanics, and muscle leverage create scaling problems that become increasingly severe as body size increases. Modern arthropods operate comfortably within these constraints, but Carboniferous giants were pushing against the absolute limits. The fossil sites that preserve evidence of these extinction processes continue to yield discoveries that refine our understanding of how environmental change drives evolutionary outcomes. Recent excavations have uncovered transitional forms that show gradual size reduction in response to changing conditions. These specimens provide direct evidence of evolution in action during periods of environmental stress. Advanced analytical techniques applied to museum collections are revealing previously hidden details about the final phases of giant arthropod evolution. Chemical analysis shows evidence of physiological stress and nutritional deficiencies in late Permian specimens. Isotopic signatures provide information about changing environmental conditions and their effects on arthropod communities. Global databases of arthropod fossils allow researchers to track extinction patterns with unprecedented precision. The data reveal that different regions experience the decline of gigantism at different times, reflecting local environmental conditions and the complex interactions between multiple stressors. This geographic perspective provides insights into the mechanisms that drove these remarkable creatures toward extinction. Modern conservation biology draws crucial lessons from these ancient extinction patterns. The gradual decline of Carboniferous giants demonstrates that species can appear stable while actually following trajectories toward extinction that won't become apparent until intervention becomes impossible. This pattern has important implications for managing contemporary species facing environmental change. Climate change research benefits from understanding how past organisms responded to atmospheric and temperature shifts. The giants provide natural experiments in how life adapts to environmental conditions very different from those that prevail today. Their responses to changing conditions offer insights relevant to predicting how modern ecosystems might respond to current environmental changes. The role of habitat fragmentation in giant arthropod extinction provides lessons directly applicable to contemporary conservation challenges. As suitable habitat became increasingly patchy during the late Permian, giant populations became more vulnerable to local disasters and genetic bottlenecks. Modern species facing similar habitat loss may be at greater risk than current population sizes suggest. Educational programs inspired by these discoveries help communicate important concepts about evolution, extinction, and environmental change. Museum exhibits featuring the giants and their extinction provide powerful examples of how environmental shifts can affect entire ecosystems over geological timescales. These displays help visitors understand both the creativity of evolution and the vulnerability of specialized organisms. Astrobiology research draws insights from Carboniferous ecosystems as examples of how life might evolve under different atmospheric conditions. The relationship between oxygen levels and biological complexity demonstrated by these ancient giants provides guidance for understanding what kinds of organisms might evolve on planets with atmospheric compositions different from modern Earth. The technological innovations developed to study these extinct giants continue to advance paleontological capabilities. New imaging techniques reveal previously invisible anatomical details. Improved chemical analysis methods extract more information from ancient specimens. Advanced computer modeling tests hypotheses about extinction mechanisms that would be impossible to evaluate through fossil evidence alone. Perhaps most importantly, the extinction of Carboniferous giants provides a powerful example of how environmental change can overwhelm even the most remarkable evolutionary achievements. These creatures had successfully exploited environmental opportunities for over 50 million years, developing biological solutions that pushed the boundaries of what seemed possible. Yet their very specialization for specific conditions made them vulnerable when those conditions changed. The patterns of survival and extinction during this transition period offer insights relevant to understanding how contemporary species might respond to current environmental challenges. Generalized organisms with broad tolerance ranges appear more likely to survive environmental shifts than highly specialized species optimized for specific conditions. This principle has important implications for conservation strategies in our rapidly changing modern world. The giant story reminds us that evolutionary success is always temporary and context-dependent. Even the most impressive adaptations are ultimately responses to specific environmental conditions that won't persist forever. The same factors that enable remarkable evolutionary achievements can become the forces that drive organisms toward extinction when conditions change. Their fossilized remains continue to inspire scientific research and public fascination as windows into a world that operated according to biological principles we're still working to understand. Each new discovery adds another piece to our understanding of how life responds to environmental opportunities and challenges. Their legacy lives on in every modern arthropod that carries genes descended from ancient lineages. Standing before these fossils today, we're witnessing more than just the remains of extinct animals. We're observing evidence of life's incredible creativity, balanced against the relentless forces of environmental change. The giants of the Carboniferous achieved something truly extraordinary, proving that evolution can produce outcomes that stretch our imagination. Their extinction teaches us about the limits that constrain even the most remarkable biological innovations. The end of their reign marked the close of one of the most ambitious experiments in the history of life on Earth. For tens of millions of years, arthropods had achieved sizes that allowed them to dominate ecosystems in ways that seem almost mythical today. Their success demonstrated that under the right conditions, invertebrates could evolve capabilities that rivaled those of much later vertebrate giants. Their story continues to unfold as new discoveries reveal additional details about their extraordinary world. Each fossil site excavated, each specimen analyzed, and each research paper published adds another chapter to our understanding of this remarkable period. The giants may be extinct, but their influence on our understanding of evolution, ecology, and environmental change remains as profound today as it was when their fossils were first discovered over a century ago. The mathematics of their existence and extinction provide lessons that extend far beyond paleontology into fields ranging from conservation biology to climate science to astrobiology. Their rise and fall illustrate fundamental principles about the relationship between organisms and their environment that remain relevant for understanding life in our rapidly changing modern world. Most significantly, the giants of the Carboniferous remind us that we live in just one moment in the long history of life on Earth, a moment when particular environmental conditions support particular kinds of organisms. Their existence shows us what was possible when conditions were different. Their extinction teaches us about the forces that continue to shape life long after any individual species has passed into the fossil record. In their magnificent rise and gradual fall, we see reflected the entire drama of evolution itself, the endless creativity of life balanced against the relentless pressure of environmental change. The giants achieved something that no arthropods before or since have accomplished, proving that the history of life is filled with extraordinary experiments that expanded the boundaries of what seemed possible. Their legacy ensures that these ancient titans remain as relevant to our understanding of life today as they were 300 million years ago, when dragonflies cast shadows like small aircraft and the very air itself was a drug that turned tiny creatures into legends. The silence that followed wasn't empty. It was pregnant with possibility, heavy with the promise of transformation. As the last giants faded into geological memory, Earth began writing new chapters in the story of life, chapters that would be dominated by creatures whose ancestors had been mere footnotes during the age of arthropod titans. The ecological vacuum left by extinct giants wouldn't remain empty for long, but filling it would require millions of years and evolutionary innovations that the Carboniferous world had never imagined. In the immediate aftermath of the end Permian catastrophe, survival belonged to the small, the adaptable, and the lucky. Tiny arthropods that had lived in the shadows of giants suddenly found themselves inheriting a world stripped bare of its former complexity. These survivors carried genetic legacies from their enormous relatives, but they would express those genes in radically different ways. The same developmental pathways that had once produced 2-meter millipedes now created creatures measured in centimeters rather than meters. Recovery was neither quick nor straightforward. For millions of years after the mass extinction, ecosystems remained impoverished shadows of their former diversity. The complex food webs that had supported multiple species of giants were replaced by simplified networks dominated by generalist survivors. Plant communities struggled to re-establish themselves in soils depleted by volcanic activity and acid rain. The intricate relationships between different trophic levels had to be rebuilt from scratch. Yet within this apparent devastation lay the seeds of extraordinary innovation. The absence of dominant large arthropods created opportunities for other lineages to explore evolutionary possibilities that had been foreclosed during the Age of Giants. Small reptiles began experimenting with increasingly sophisticated terrestrial adaptations. Early archosaurs developed new hunting strategies and locomotory innovations. The stage was being set for the rise of dinosaurs, though that evolutionary drama was still millions of years in the future. The atmospheric changes that had doomed the giants were simultaneously creating conditions favorable for different kinds of organisms. Lower oxygen levels, while challenging for creatures adapted to hyperoxic conditions, were more compatible with active metabolic strategies employed by vertebrates. The variable climate patterns associated with Pangaea's continental configuration favored organisms capable of behavioral and physiological flexibility rather than those optimized for stable conditions. Marine ecosystems underwent their own profound transformations during this transitional period. The shallow seas and coastal wetlands that had supported aquatic phases of giant arthropod life cycles were replaced by different marine environments with altered chemistry and biological productivity. New groups of marine organisms began to exploit ecological niches that had been unavailable during the Carboniferous, setting the stage for the spectacular marine radiations of the Mesozoic era. The plant kingdom was simultaneously undergoing revolutionary changes that would fundamentally alter terrestrial ecosystems. The dominance of spore-bearing plants that had characterized Carboniferous forests was giving way to seed plants with new defensive strategies and growth patterns. These botanical innovations would create different opportunities and challenges for herbivorous arthropods, driving evolutionary pressures towards specialization rather than gigantism. Early conifers and other gymnosperms developed increasingly sophisticated chemical defenses that made plant material more difficult to digest and process. The abundant, easily digestible organic matter that had supported creatures like Arthropleura was being replaced by plant tissues rich in resins, tannins, and other compounds that required specialized digestive adaptations to utilize effectively. This chemical arms race between plants and herbivores would become one of the driving forces of post-Paleozoic evolution. The soil ecosystems that formed in this new world were fundamentally different from those that had existed during the Carboniferous. The massive amounts of organic matter that had accumulated in coal swamps were no longer being produced at comparable rates. Decomposition processes became more efficient as new groups of bacteria and fungi evolved to break down the chemically defended plant materials that were becoming increasingly common. Arthropod evolution during the Triassic recovery period followed pathways that emphasized efficiency and specialization over raw size. The survivors that gave rise to modern insect diversity developed increasingly sophisticated adaptations for exploiting specific ecological niches. Rather than competing directly with vertebrates for dominance through size and power, arthropods succeeded by becoming masters of specialization, developing capabilities that larger organisms couldn't match. The evolution of complete metamorphosis in insects represents one of the most significant innovations to emerge from this post-extinction recovery period. This developmental strategy allowed arthropods to exploit different resources during larval and adult phases, effectively doubling their ecological versatility. The larvae could specialize for growth and nutrient acquisition, while adults focused on reproduction and dispersal, a division of labor that proved extraordinarily successful. Social evolution in arthropods also accelerated during this period, leading to the sophisticated societies seen in modern ants, bees, and termites. These colonial organisms achieved ecological dominance not through individual size, but through collective action and division of labor. A single ant colony could process resources and modify environments in ways that rivaled the ecological impact of much larger individual organisms. The respiratory innovations that had once supported giants were refined and adapted for different purposes in smaller organisms. Modern insects developed incredibly efficient gas exchange systems that allowed them to maintain high metabolic rates despite their small size. The same basic tracheal breathing mechanism was optimized for rapid oxygen delivery to support the energetic demands of flight, complex behaviors, and sophisticated physiological processes. Nervous system evolution in post-extinction arthropods emphasized information processing efficiency over raw computational power. Modern insect brains contain relatively few neurons compared to vertebrate brains, but those neurons are organized in ways that allow remarkable behavioral complexity. The navigation abilities of bees, the communication systems of ants, and the predatory precision of dragonflies all represent pinnacles of neural efficiency achieved through evolutionary refinement rather than scaling. The development of powered flight in insects reached new levels of sophistication during the recovery period. Modern flying insects can achieve maneuvers that would have been impossible for the giants of the Carboniferous, despite their smaller wing areas and reduced power-to-weight ratios. Advanced wing kinematics, sophisticated flight muscles, and precise neural control systems allow contemporary insects to hover, accelerate rapidly, and execute complex aerial maneuvers that exceed the capabilities of their ancient predecessors. Reproductive strategies in modern arthropods reflect the evolutionary lessons learned from the extinction of giants. Rather than investing heavily in individual offspring that require extended development periods, most contemporary insects produce large numbers of rapidly developing young that can quickly adapt to changing environmental conditions. This reproductive strategy provides resilience against environmental perturbations that proved fatal to species with longer generation times. Chemical communication systems in modern arthropods represent another innovation that emerged from the post-extinction recovery. Pheromones allow insects to coordinate complex behaviors, locate mates across large distances, and share information about food sources and environmental conditions. These chemical signals enable sophisticated social coordination without the energetic costs of maintaining large body sizes or complex neural structures. The coevolutionary relationships between insects and flowering plants that developed during the Mesozoic era created new ecological opportunities that were unavailable to Carboniferous giants. Pollination mutualisms, herbivore-plant interactions, and seed dispersal relationships generated complex webs of evolutionary feedback that drove increasing specialization and diversification in both plant and arthropod lineages. Modern arthropod diversity represents the ultimate expression of post-extinction evolutionary innovation. With over 1 million described species, insects alone comprise more than half of all known animal species. This extraordinary diversity reflects evolutionary strategies that emphasize ecological specialization, rapid reproduction, and efficient resource utilization, rather than the size-based dominance that characterized their ancient relatives. The biomechanical principles that constrained Carboniferous giants continue to influence modern arthropod evolution, but within very different size ranges. Contemporary insects operate well within the scaling limits that doomed their ancient relatives, allowing them to exploit the full range of ecological opportunities available to organisms with external skeletons and passive respiratory systems. Physiological innovations in modern arthropods include sophisticated mechanisms for dealing with environmental stress, seasonal variation, and resource scarcity. Many species can enter dormant states during unfavorable conditions, modulate their metabolic rates in response to temperature changes, and rapidly adjust their behavior to exploit temporary resource opportunities. These capabilities provide the flexibility that was lacking in the highly specialized giants of the Carboniferous. The ecological roles filled by modern arthropods extend far beyond those occupied by their ancient predecessors. Contemporary insects serve as pollinators, decomposers, predators, herbivores, and ecosystem engineers in ways that were impossible during the Age of Giants. Their small size and high reproductive rates allow them to respond rapidly to environmental changes and exploit ephemeral resources. Technological advances in studying modern arthropods continue to reveal new insights about their capabilities and evolutionary relationships to extinct giants. High-speed photography of insect flight reveals biomechanical principles that help explain both the achievements and limitations of ancient flying arthropods. Molecular analysis of modern species provides information about evolutionary relationships and the genetic basis of adaptations that emerged during the post-extinction recovery. Experimental studies of modern arthropods in controlled atmospheric conditions help validate hypotheses about the relationship between environmental factors and body size evolution. These experiments confirm that oxygen availability does influence arthropod physiology and performance, supporting the atmospheric explanation for Carboniferous gigantism, while also revealing the complex interactions between multiple environmental variables. Conservation efforts focused on protecting modern arthropod diversity draw important lessons from the extinction patterns that ended the Age of Giants. The extraordinary specialization that makes contemporary insects so successful also makes them vulnerable to environmental changes, that disrupt their specific ecological requirements. Understanding these vulnerabilities helps guide efforts to preserve arthropod diversity in rapidly changing modern environments. Climate change research incorporates insights from arthropod evolutionary history to predict how contemporary species might respond to ongoing environmental shifts. The patterns of survival and extinction that characterize the transition from the Paleozoic to Mesozoic eras provide guidance for understanding which modern species are most likely to persist through current environmental changes. Agricultural science benefits from understanding the evolutionary innovations that make modern arthropods such successful colonizers and adaptable organisms. The same capabilities that allow insects to exploit diverse ecological niches also make them effective agricultural pests and disease vectors. Understanding their evolutionary strengths helps in developing sustainable management strategies. Biomimetic engineering draws inspiration from the sophisticated adaptations of modern arthropods that evolved from the ashes of ancient giants. The efficient flight mechanisms of insects, their sophisticated sensory systems, and their chemical communication networks provide models for developing new technologies. These applications represent a continuation of the innovative spirit that characterized arthropod evolution throughout their long history. Educational programs that connect the story of extinct giants with the diversity of modern arthropods help communicate important concepts about evolution, extinction, and recovery. Understanding how life rebuilt itself after the Permian catastrophe provides perspective on the resilience of biological systems and the creative potential of evolutionary processes. The study of modern arthropod development provides insights into the genetic and developmental mechanisms that control body size and could have enabled gigantism in ancient species. Experimental manipulation of developmental pathways in laboratory insects reveals the genetic switches that regulate growth and could potentially be modified to produce larger organisms under appropriate environmental conditions. Evolutionary developmental biology research using modern arthropods as model systems helps explain how the complex body plans of ancient giants could have evolved from simpler ancestral forms. Understanding the genetic basis of segmentation, appendage development, and organ system formation provides insights into the evolutionary processes that produce the remarkable diversity of Carboniferous arthropods. Ecological research in modern ecosystems reveals the complex interactions between arthropods and other organisms that were probably important in ancient ecosystems as well. Studies of predator-prey relationships, competitive interactions, and mutualistic associations provide models for understanding how giant arthropods fit into the ecological networks of their time. Paleoenvironmental reconstruction techniques continue to refine our understanding of the conditions that supported ancient giants and drove their eventual extinction. Improved methods for analyzing ancient atmospheric composition, temperature patterns, and ecosystem structure provide increasingly detailed pictures of the world that these remarkable creatures inhabited. International collaborations between researchers studying both fossil and modern arthropods create comprehensive databases that span hundreds of millions of years of evolutionary history. These datasets reveal long-term patterns in arthropod evolution and help identify the factors that have consistently influenced their success and failure over geological timescales. The story of arthropod recovery from the Permian extinction continues to unfold as new fossils from Triassic deposits reveal the early stages of post-extinction diversification. These specimens show how surviving lineages began to explore new ecological opportunities and develop the innovations that would eventually lead to modern arthropod diversity. Museum collections of both fossil and modern arthropods serve as repositories of evolutionary history that support ongoing research and education. These collections document the transition from ancient giants to modern diversity and provide the specimens necessary for comparative studies that reveal evolutionary patterns and processes. Public interest in both extinct giants and modern arthropod diversity helps support scientific research and conservation efforts. Popular fascination with creatures like Meganeura and Arthropleura creates opportunities to communicate important scientific concepts about evolution, ecology, and environmental change to broad audiences. The giants are gone, but their legacy lives on in every dragonfly that skims across a pond and every millipede that crawls through autumn leaves. They proved that when Earth's chemistry aligns with evolutionary opportunity, life can achieve the impossible. Their story reminds us that we're just visitors in an ever-changing world, where even the most magnificent adaptations are temporary gifts. The next time you see a beetle or watch a butterfly, remember you're witnessing the descendants of legends, creatures that carry the genetic echoes of titans in their tiny frames. Thanks for joining me on this journey through deep time, and I'll catch you in the next one.